Black holes have always been the monsters of the universe's tales. They are dark, bottomless pits that crush stars, twist time itself, and swallow anything that drifts too close. But what if black holes are not the ultimate story of extreme gravity? What if something even stranger is hiding in the shadows, something that challenges everything we know about space, time, and even the idea of death? That something is the Gravastar. Unlike a black hole, it does not have a singularity at its centre. Instead, its heart is filled with dark energy, surrounded by a shell made of bizarre, exotic matter. There is no event horizon, no point of no return, only a strange throbbing core that might keep the information black holes seem to erase. Could Gravastars be what black holes eventually turn into, or perhaps what they have been all along? Before we start, let us know where in the world you're watching from and what time it is there. Get ready for an amazing space journey. Gravastars are one of the strangest and most fascinating ideas ever to come out of modern physics. The word itself is short for gravitational vacuum star, and just hearing the name makes you think of something mysterious and cosmic. They are often brought up in conversations about black holes, because on the surface they seem to be a possible alternative to them. To really understand what a gravastar is, we have to go back to the long history of black holes themselves, because black holes have always been the giants in the world of cosmic mysteries. They are the monsters of space, regions so dense and so powerful that not even light itself can get away from them once it falls in. For centuries, scientists and philosophers alike have wondered what happens to matter when gravity crushes it beyond recognition, and gravastars are one possible answer to that question. The idea of gravastars came into being in the early 2000s, when physicists began questioning whether black holes were the only possible outcome of a star collapsing under its own gravity. For a long time, the black hole seemed like the unavoidable final chapter of a massive star's life. When a star many times heavier than our Sun runs out of nuclear fuel, it can no longer push back against the crushing force of its own gravity. The outer layers fall inward, the core implodes, and if the star is heavy enough, not even the formation of a neutron star can stop the collapse. The result, according to traditional physics, is a black hole. This is a place where gravity is so extreme that space and time themselves break down. At the centre lies the so-called singularity, a point of infinite density where the known laws of physics simply stop working. For many scientists, that conclusion always felt unsatisfying. How could the laws of nature that work everywhere else in the universe suddenly fail here? Shouldn't there be a different explanation? One that avoids the uncomfortable infinity at the heart of a singularity? That is where gravastars enter the picture. A gravastar is proposed as an object that looks very much like a black hole from the outside, but is very different on the inside. Instead of having a singularity hidden behind an event horizon, a gravastar would have something more exotic, something that might even solve some of the biggest puzzles in physics. The key idea is that when a star collapses, it may not always form a singularity. Instead, under some conditions, the collapse could stop just short of creating a black hole. The matter of the star could be transformed into something entirely new, forming a shell around a strange kind of space filled not with matter, but with vacuum energy. This is a strange form of energy that physicists believe fills the universe itself, tied to the idea of dark energy that pushes the cosmos to expand faster and faster. Inside a gravastar, this vacuum energy would balance the crushing force of gravity, holding the object stable and preventing a singularity from ever forming. From the outside to telescopes and detectors, a gravastar would look so similar to a black hole that it would be almost impossible to tell them apart. But if you could peel it open and look inside, you would see something radically different. To grasp how radical this difference is, we have to step back and look at what makes a black hole so special. A black hole is defined by its event horizon, the invisible boundary that marks the point of no return. Cross it, and you are trapped forever. No signal, no particle, not even light, can escape once it passes this horizon. At the centre of this trap lies the singularity, a point where gravity has crushed matter to zero size and infinite density. The laws of physics as we know them no longer make sense here. That has always been the troubling part of black hole theory. Scientists generally dislike infinities because they signal that our theories are incomplete. A gravastar avoids this problem by removing the singularity altogether. Instead of an infinite point, there is a bubble of vacuum energy. Instead of an event horizon that traps light forever, there may be a kind of thin shell of matter, incredibly dense and strange, that holds the structure together. In other words, a gravastar would mimic a black hole's appearance without actually being one. This difference is not just a small technical point. It has enormous consequences for how we think about the universe. If gravastars are real, they would solve what is called the information paradox of black holes. According to quantum physics, information about matter cannot be destroyed, but black holes seem to erase information when they swallow it. If gravastars exist, the information might not be destroyed at all, but instead stored in their shell or somehow preserved in the vacuum energy interior. This could reconcile two of the biggest frameworks in science: general relativity, which describes gravity and the large-scale universe, and quantum mechanics, which rules the tiny world of atoms and particles. The two have long clashed when it comes to black holes, but gravastars might offer a bridge. The concept of gravastars first gained attention around the year 2001, when physicists Powell Mazur and Emil Motola suggested them as an alternative to black holes. They argued that instead of collapsing into a singularity, matter might undergo a phase transition, much like water freezing into ice, but on a cosmic scale. In this transition, the interior of the collapsing star would become a kind of vacuum state, while the outer layers would form an ultra-dense shell. This structure would be stable and could mimic the external gravitational pull of a black hole so closely that astronomers might not be able to tell the difference. To an outside observer, light bending around the object, matter swirling into it, and even the way it influences nearby stars would look almost identical to a black hole. But beneath the surface, the physics would be entirely different. Explaining this in simple terms, you could think of a gravastar as a cosmic trickster. From a distance, it wears the mask of a black hole, pulling in matter and light with nearly the same strength. But inside, it hides something else, something less violent, something that does not involve ripping the fabric of the universe into a singular point. The vacuum energy at its core acts like a spring pushing outward, balancing the inward pull of gravity. The result is an object that sits right at the edge of becoming a black hole but never quite crosses that final step. It is a balancing act, a stalemate between forces that would otherwise lead to total collapse. One of the reasons gravastars are so intriguing is that they might explain some puzzling observations in astronomy. Black holes are thought to power quasars, the extremely bright centers of distant galaxies, as well as many of the X-ray sources we see in the sky. But in some cases, the data does not perfectly match what black hole models predict. Gravastars could offer an explanation, because they might behave slightly differently, especially when it comes to how they radiate energy and how they interact with matter falling toward them. For example, when matter falls onto a gravastar's shell, it might create bursts of energy that differ from those produced by a black hole's accretion disk. Detecting such differences would be one of the ways to test if gravastars exist. Still, it is important to be clear that gravastars are, as of now, a theoretical idea. No one has yet found definitive evidence of one. Every candidate object we know that looks like a black hole could either truly be a black hole or in theory a gravastar. Our instruments are not yet precise enough to distinguish between the two in most cases. The real challenge is that from the outside they behave so similarly. Both have extreme gravitational pulls, both can bend light dramatically, and both can anchor powerful cosmic jets. The only way to tell them apart would be to study tiny details in the way they emit radiation, or perhaps in the gravitational waves they produce when they merge. Some scientists have even suggested that future detectors might catch a subtle echo in gravitational wave signals that would reveal a gravastar instead of a true black hole. These echoes would come from waves bouncing off the gravastar's surface, instead of being swallowed by an event horizon. The idea of gravastars also sparks the imagination when we think about the broader universe. If gravastars exist, they could be scattered throughout galaxies, quietly masquerading as black holes. They could lurk at the centers of galaxies driving cosmic evolution, or they could be hiding in binary systems, feeding off companion stars just like black holes do. Even the giant object at the center of our Milky Way, known as Sagittarius A star, could, in principle, be a gravastar instead of a black hole. We simply do not know for sure yet. The differences between gravastars and black holes also highlight the way science constantly evolves. For most of the 20th century, black holes were themselves only theoretical. When Albert Einstein's equations first hinted at them in the early 1900s, even Einstein himself doubted they could be real. They sounded too extreme, too strange, like a mathematical curiosity rather than a real object. It was only decades later, when evidence piled up, that black holes became accepted as genuine parts of the cosmos. Today, we not only believe in them, we have even imaged one directly with the Event Horizon Telescope in the year 2019. The glowing ring of matter around the supermassive black hole in the galaxy M87 was one of the most dramatic confirmations of Einstein's theory ever seen. But just as black holes went from speculation to observation, gravastars might follow a similar path. What seems strange and exotic today could turn out to be part of the real universe tomorrow. Another way to look at gravastars is to consider how they challenge our sense of extremes. Black holes are often described as the ultimate endpoints of matter. Nothing can escape them, nothing survives inside them, and time itself is distorted beyond recognition. Gravastars, however, suggest that maybe nature has another trick up its sleeve, a way of avoiding the harshness of singularities while still creating objects of immense power. They remind us that the universe is not always as simple as the first explanations we come up with. There could be layers of complexity we have not yet discovered, and gravastars might be one of those hidden layers. The possibility of gravastars also touches on the fate of information, one of the deepest puzzles in physics. If black holes truly destroy information, that would break one of the fundamental rules of quantum mechanics. Scientists like Stephen Hawking wrestled with this paradox for decades, and it led to some of the most heated debates in theoretical physics. Gravastars neatly sidestep the issue by providing a place for information to be stored or preserved, making them very attractive to physicists looking for consistency. In this sense, gravastars are not just about stars and collapse, they are about the very foundations of how reality works. On a more imaginative level, thinking about gravastars raises philosophical questions as well. What does it mean if the most terrifying objects in the universe, the black holes that have haunted science fiction and science fact alike, are not the final word? What if they are shadows of something deeper, a hint at new physics waiting to be uncovered? Gravastars suggest that the universe might be playing a cosmic trick on us, showing us one face while hiding another. They invite us to look closer, to question what we think we know, and to keep pushing the boundaries of discovery. So, to define the concept as simply as possible, a gravastar is a hypothetical object that forms when a collapsing star stops just short of becoming a black hole. Instead of forming a singularity and an event horizon, it forms a shell of exotic matter surrounding a core filled with vacuum energy. From the outside, it acts almost exactly like a black hole, but on the inside, it is something else entirely. The difference between the two is like the difference between a locked room with no exit and a sealed bubble filled with strange light. Both are mysterious, but one hides a dead end, while the other hides something new. Gravastars remain a theory, a possibility rather than a proven reality. The story of the gravastar is one of those rare moments in science where imagination, boldness, and a willingness to question the most accepted ideas all came together. To understand how this idea was born, we need to step back into the late 20th century, a time when the study of black holes was already booming with discoveries and debates. Black holes had moved from being strange mathematical solutions written on paper in the early years of Albert Einstein's theory of general relativity to being treated as real, physical objects scattered across the universe. By the end of the 20th century, astronomers had already gathered strong evidence that black holes were not just abstract theories, but true celestial monsters. They found stars moving around invisible companions, they detected enormous bursts of X-rays coming from regions where matter was falling into invisible pits, and they saw signs of huge gravitational forces bending space itself. To most of the scientific world, it seemed beyond doubt that black holes were real. But science is never as simple as everyone agreeing on one neat answer. In fact, it thrives most when people dare to question the obvious truths. And this is where the story of the gravastar begins. In the year 2001, two physicists, Paul O. Mazur from the University of South Carolina and Emil Motola from the Los Alamos National Laboratory, put forward a new and daring idea. They proposed that what astronomers had been calling black holes might not be black holes at all. Instead, these terrifying objects might be something stranger, something that had never been imagined before, a gravastar. The name gravastar itself is short for gravitational vacuum star. It sounds almost poetic, yet also mysterious. What Mazur and Mottola were really suggesting was that nature might be playing a trick on us. The universe might be showing us something that looks like a black hole, behaves like a black hole, and even fools us into thinking it is one. But at its core, it is actually a very different kind of object. To appreciate how daring this idea was, it helps to know just how deeply rooted the belief in black holes had become. From the 1960s onward, physicists like John Wheeler, Roger Penrose, and Stephen Hawking had made the concept of black holes central to modern astrophysics. By the 1990s, black holes had almost become household names, appearing in science books, movies, and even children's stories. They were symbols of the most extreme and unshakable laws of the cosmos. Yet Mazur and Mottola were not satisfied with the black hole picture. They looked closely at the mathematics of Einstein's general relativity and began to see problems that made them uneasy. A black hole, as normally described, has at its centre what is called a singularity, a point where density and gravity become infinite. But infinity in physics is usually a sign that something is wrong, a signal that our equations have gone beyond their proper limits. The singularity at the heart of a black hole is not really a physical object, but rather a breakdown of our theories. And Mazur and Mottola asked themselves, should we really believe that nature allows such a breakdown? Should we accept that physics ends at the core of a black hole, or should we search for another explanation? Their answer was bold. They suggested that instead of collapsing into a singularity, a star that dies in extreme gravity might take on another form. In their model, the collapsing matter does not crush itself into an infinitely small point, but instead undergoes a kind of phase transition, almost like water freezing into ice or steam condensing into liquid. In this process, the inside of the star becomes a strange state of matter, dominated not by normal particles, but by what physicists call vacuum energy. This energy is linked to the idea of dark energy, the mysterious force that drives the expansion of the universe. What Mazur and Mottola proposed was that the core of a collapsed star could be filled with this exotic energy, forming a bubble of repulsive pressure that prevents the singularity from ever forming. Around this bubble there would be a very thin shell of extremely dense matter, almost like a cosmic skin holding the structure together. To an outside observer, this gravastar would look very much like a black hole. Light and matter falling toward it would disappear from view, time would seem to slow near its edge, and its gravity would be almost impossible to resist. But unlike a black hole, a gravastar would not have a singularity, and would not contain an event horizon in the same way. Instead, it would have a surface, an actual boundary, although this surface would be so extreme that it would be almost impossible to detect directly. This was the birth of the gravastar theory, a bold proposal in the year 2001 by two physicists who dared to challenge the most feared object in the universe. It was more than just a new model. It was a statement that our understanding of gravity, of energy, and of the deep structure of space and time might still be incomplete. The timing of their idea is also worth noting. The early 2000s were years when cosmology was going through a revolution. In the year 1998, astronomers had discovered that the expansion of the universe was not slowing down as everyone had expected, but speeding up. This shocking finding led to the idea of dark energy, a mysterious force that seemed to make up most of the cosmos. Suddenly, the concept of exotic forms of energy was no longer just abstract speculation. It was real science, supported by observation. Mazur and Mottola were therefore proposing gravastars at exactly the moment when physicists were beginning to take seriously the idea that vacuum energy and dark energy might play huge roles in the universe. It is important to understand the personalities behind this theory as well. Pavel Mazur was known for his bold thinking and his willingness to explore unorthodox ideas. Emil Mottola had a background in theoretical physics and had worked on problems in quantum field theory and gravity. Both of them were respected scientists, yet they were not afraid to walk a path that many of their colleagues might have considered too risky. In fact, when they first published their papers on gravastars, the reaction was mixed. Some physicists admired the creativity and daring of the idea, while others dismissed it as too speculative too strange, or even unnecessary. Why replace black holes with something so complicated, many asked, when black holes already seem to explain the observation so well? But science is not about always finding the quickest or simplest answer. It is about exploring possibilities, even if they seem strange at first. The Gravastar idea stood as a reminder that black holes, for all their fame, were still not completely understood. After all, nobody had ever truly seen a black hole itself. What astronomers had observed were the effects around black holes, the motion of stars, the glow of hot gas, the bending of light, but never the object directly. And if appearances could be deceiving, then maybe Gravastars were hiding in plain sight. In the years that followed their proposal, the Gravastar idea continued to stir debate. Other physicists began to explore its consequences, asking whether Gravastars could really form in nature, how they would evolve, and whether they could be distinguished from black holes by observations. Some tried to connect Gravastars with other exotic objects, such as boson stars or dark energy stars, exploring whether these might all be different sides of the same coin. In this way, the Gravastar theory became part of a larger conversation about what really happens when gravity reaches its most extreme limits. The birth of the Gravastar idea, then, was not just about two scientists writing a paper. It was about a turning point in how we think about the universe. It was about daring to ask whether the most terrifying monsters in the cosmos might actually be illusions, disguises hiding something even stranger. It was about questioning whether the universe is still holding secrets that we have not yet unwrapped. Looking back, it is fascinating to think that this all began in the early years of the 21st century, when humanity was just beginning to map the universe with new telescopes, satellites, and instruments capable of peering deeper into space than ever before. The Gravastar was born in that atmosphere of discovery, uncertainty, and wonder. And while the debate about Gravastars versus black holes is still far from settled, the very fact that the idea exists reminds us of the essence of science, that every answer opens the door to new questions, and that even the darkest corners of the cosmos might not be what they seem. The physics behind Gravastars is one of the most fascinating areas of modern thought in astrophysics and theoretical physics. It combines the deep ideas of Albert Einstein's general relativity with the strange and almost ghostly concept of vacuum energy, which is linked to quantum mechanics and the structure of space itself. To understand Gravastars, one must first stretch the mind to accept realities that at first sound impossible, because they live at the edge of our knowledge of the universe, where the familiar laws of nature seem to bend and even break. Gravastars were proposed as alternatives to black holes, and the reasoning behind them is built on both the known rules of gravity and the less understood but equally important rules of quantum fields and energy. By exploring how general relativity and vacuum energy meet, the strange physics of Gravastars begins to unfold. General relativity is the key to understanding the gravity that governs stars, galaxies, planets, and the universe itself. Before Einstein, gravity was explained by Isaac Newton as a force between objects that had mass, and for centuries this explanation worked well. But Einstein showed in the early years of the 20th century that gravity was not a force in the usual sense, but rather the result of the bending of space and time. When something heavy like a star or planet exists, it curves the very fabric of space-time around it, and other objects move along those curves. This is why Earth circles the Sun, not because it is being pulled by an invisible string, but because the Sun bends space-time so that Earth follows a curved path that looks like an orbit. This idea becomes even stranger when we talk about extreme objects like neutron stars and black holes. These are the corpses of stars that used up their nuclear fuel and collapsed under their own gravity. A neutron star is already unimaginably dense, with the mass of more than one sun squeezed into a ball only about 20 kilometers across. But when the collapse cannot be stopped, the theory of general relativity predicts that the star shrinks into a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. The edge of this region is called the event horizon. Once anything crosses it, it is lost forever. The math of relativity says that at the very center of a black hole lies a singularity, a point of infinite density where the known laws of physics break down. The idea of a singularity is both powerful and troubling. Physicists often take it as a sign that our understanding is incomplete. Infinite density is not something nature should allow so easily. This is where the idea of gravastars enters. Gravastars, short for gravitational vacuum stars, were suggested as objects that look from the outside almost exactly like black holes, but without the troubling singularity at their centre. Instead of collapsing all the way into a point, the matter of the star would trigger a strange transition in spacetime itself, producing a core filled with vacuum energy. This idea offers a way to use the mathematics of general relativity while avoiding the puzzle of infinities. Vacuum energy is one of the strangest concepts in physics, and to understand gravastars it must be explained clearly. Normally, people think of a vacuum as empty space, a void with nothing in it. But quantum mechanics tells us that even the emptiest space is not truly empty. It seethes with invisible activity, with particles and antiparticles popping in and out of existence for the tiniest fractions of a second. This restless background is called quantum fluctuations, and the energy tied to it is called vacuum energy. It is a kind of latent power hidden within space itself, and although it cannot be directly seen, its effects are very real. One famous example of vacuum energy is the Casimir effect, where two metal plates placed very close together in a vacuum experience an attractive force, not because of any electrical charge, but because the vacuum between them is altered by the plate's presence. This shows that empty space has measurable physical effects. On the larger scale, vacuum energy is also thought to be linked to dark energy, the mysterious force that is pushing the universe to expand faster and faster. Now, when we take general relativity and add in the possibility of vacuum energy, a new picture forms. Instead of a collapsing star shrinking into a singularity, what if the collapse reached a point where space-time itself changed state, like water freezing into ice? The inside of the star could transform into a bubble of vacuum energy, a region of space where negative pressure counteracts the pull of gravity. This bubble would be surrounded by an incredibly thin but extremely dense shell of matter. The shell would act like a boundary, holding the vacuum core inside and balancing the gravitational pull from outside. The result would be a gravastar. From far away, a gravastar would be nearly indistinguishable from a black hole. It would have an enormous gravitational field, and light passing near it would be bent in almost the same way. To an outside observer, it would appear dark and menacing, because the shell would absorb or trap nearly all light. But at its heart, instead of a singularity, there would be a region filled with vacuum energy, perfectly smooth and free of infinities. This resolves one of the biggest problems with black holes, the issue of the singularity. Another reason gravastars are interesting is because of the way they connect with the problem of information. Black holes famously raise the question of whether information can be lost. According to quantum mechanics, information about the state of particles can never be destroyed. But when things fall into a black hole and cross the event horizon, they seem to vanish forever. Stephen Hawking showed that black holes can slowly evaporate by releasing what is now called Hawking radiation. But even then, the fate of the information remains unclear. Gravastars might offer a way around this paradox. Since they do not have a singularity, and since their surface is a real physical shell rather than a point of no return, it is possible that information falling into a gravastar could be stored in or interact with this shell, avoiding the deep paradox of information loss. To make this clearer, one can think of the difference between a soap bubble and a solid ball. A black hole is like a ball with a dark and inaccessible core. A gravastar, on the other hand, is more like a bubble, with a thin but strong skin surrounding a strange interior. The skin, or shell, does all the work of holding things together, while the inside is an exotic vacuum state. Of course, the mathematics behind this is complex. General relativity provides the equations to describe how mass and energy curve space-time. The vacuum energy provides a term in these equations that represents a constant negative pressure. By balancing these effects, physicists can construct theoretical solutions that describe gravastars. One of the key ideas is that the negative pressure inside the gravastar acts in opposition to the normal pressure of matter trying to collapse. In this way, the inward pull of gravity is resisted and equilibrium is reached. The negative pressure of vacuum energy is crucial here. Unlike ordinary matter or radiation, which exert positive pressure and add to gravitational collapse, vacuum energy pushes outward. It is the same kind of effect that causes the expansion of the universe to accelerate. Inside a gravastar, this pressure balances the star's gravity perfectly at the shell, Without it, the collapse would continue without end. Another fascinating aspect of Gravastars is the possibility that they could form naturally in the universe. If a massive star collapses, and under certain conditions the collapse causes a transition of space-time into this exotic vacuum state, then a Gravastar could form instead of a black hole. This means that some of the objects we think are black holes might in fact be Gravastars. Since from the outside they look so similar, it is extremely difficult to tell the difference. But careful studies of gravitational waves, or perhaps the detailed radiation coming from the region around such objects, might one day reveal a clue. In 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, first detected gravitational waves from merging black holes, some physicists wondered if they could also detect the subtle signature of merging Gravastars. The ripples in space-time from such collisions might differ in very small but important ways. For example, if a Gravastar lacks a true event horizon, the waves might echo differently after the collision. Some scientists even search for these echoes in the data, though the results are not yet clear. If one day these signals are found, it could point to the existence of Gravastars and change our whole understanding of cosmic collapse. The role of vacuum energy in Gravastars also links them to cosmology. The same strange energy that fills their interior is also thought to drive the expansion of the entire universe. It is remarkable to think that the same force shaping the fate of stars could also be shaping the fate of the cosmos itself. In fact, the equations describing a Gravastar's interior are very similar to those describing the universe during its early moments of inflation, when vacuum energy made space expand at an almost unbelievable rate. This connection hints that Gravastars are not just exotic star remnants, but perhaps windows into the deepest laws of physics. There are still many open questions. Some physicists argue that Gravastars are elegant in theory, but may never exist in reality, because the conditions needed to form them may be too specific. Others think that nature often surprises us, and that the universe may prefer Gravastars over singularities, because they avoid infinities and paradoxes. It is possible that with more data from gravitational waves, or with sharper images from telescopes like the Event Horizon Telescope, we will one day be able to tell whether the supermassive dark objects at the centres of galaxies are black holes or Gravastars. When one reflects on the physics behind Gravastars, it is clear that they are more than just alternatives to black holes. They are a meeting place of two of the greatest theories in science, general relativity and quantum physics. General relativity provides the rules for how space-time bends and collapses under gravity, while quantum theory provides the idea of vacuum energy, the restless sea of energy that never goes away. Gravastars exist in the imagination of scientists at the point where these two worlds collide. To explore Gravastars is to explore both the grand scale of the cosmos and the smallest fluctuations of the quantum vacuum. It requires thinking of stars not as simple balls of matter, but as stages where the very laws of physics perform a complex play. If Gravastars exist, they are not just dead stars. They are monuments to the hidden power of space itself, objects that hide a bubble of the universe's deepest energy behind a thin, dense shell. Black holes have for many decades been seen as the ultimate monsters of the universe, the endpoint of gravity taken to its most terrifying extreme. They are the places where space and time collapse into something so warped that nothing, not even light, can escape their grasp. Gravastars, on the other hand, are a far stranger and more subtle idea, proposed not as a fantasy, but as a serious alternative to black holes. To understand the ongoing debate between black holes and Gravastars, one must not only explore their similarities and differences, but also the reasons why scientists still do not fully agree on which of these cosmic objects may actually exist. In order to do this, it is important to begin by carefully unfolding what makes a black hole what it is, what a Gravastar is supposed to be, and why the two are sometimes so difficult to tell apart yet so profoundly different in their nature. A black hole is born when a very massive star runs out of fuel. The nuclear reactions that once fought against gravity's inward pull cease, and the star collapses under its own weight. If the star is massive enough, several times the mass of our Sun, then nothing can stop the collapse. The star is crushed to an infinitely dense point called a singularity, wrapped inside an event horizon. The event horizon is the ultimate boundary, the surface around the black hole beyond which nothing can return. To an outside observer, the black hole looks like a region of space where light disappears, as though space itself has been torn into a dark well. Time slows down near its surface, and physics itself reaches the edges of what we understand. This picture of the black hole comes directly from Albert Einstein's general theory of relativity, published in the year 1915, and ever since then astronomers and physicists have been trying to understand the exact details of these fascinating but frightening objects. A gravastar, whose name comes from the phrase gravitational vacuum star, is not as well known but is in many ways just as mind-bending. The concept was proposed in the early years of the 21st century by physicists Pavel Mazur and Emil Mottola. They asked a bold question: what if what we call black holes are not black holes at all, but something else entirely, something that only looks like a black hole from the outside? In their theory, when a star collapses under its own weight, it does not form a singularity and an event horizon. Instead, the collapse stops just short of those extreme conditions. A gravastar, in their description, has a very thin outer shell made of extremely dense material, but inside that shell, rather than a singularity, is a core filled with exotic energy that has negative pressure, something like the energy that scientists believe is causing the expansion of the universe. This inner vacuum energy balances the outward push against the inward pull of gravity, creating a stable object that looks, to a distant observer, almost exactly like a black hole. But it is not one. There is no singularity at the center, and there is no event horizon. That means that information and energy are not lost forever inside it, and this has enormous consequences for physics. When comparing black holes and gravastars, one can begin with their similarities. Both are born from the collapse of very massive stars, and both are incredibly compact. Their gravitational pull is so intense that they curve the paths of light and distort the geometry of space around them. For an astronomer observing them from far away, both black holes and gravastars would look like dark, compact objects surrounded by swirling matter, with gas and dust heating up as it falls toward them and shining in X-rays and radio waves. Both can power quasars and active galactic nuclei, some of the brightest beacons in the universe. Both can also produce gravitational waves when they collide with one another, sending ripples through space-time that can be detected here on Earth. In other words, black holes and gravastars are observationally very hard to tell apart. For all practical purposes, if one were to look at the center of our own Milky Way galaxy, where a dark mass 4 million times the mass of our Sun sits, one could not be sure whether it is a black hole or a gravastar. The observations would look nearly the same, but once one looks deeper, the differences between the two become immense. A black hole has an event horizon, a point of no return. A gravastar does not. A black hole hides a singularity, where density and curvature go to infinity, while a gravastar replaces that nightmare with a strange but manageable core of vacuum energy. A black hole eats everything that comes too close, trapping light and information forever. A gravastar may appear to swallow matter, but in theory, because there is no horizon, that matter might be able to interact with the shell, or even leave in some form. A black hole violates many of the usual principles of physics, such as the preservation of information, leading to what is known as the information paradox. A gravastar, in contrast, might offer a way out of this paradox by avoiding the singularity altogether. In essence, a gravastar is an attempt to heal the contradictions that arise when black holes are pushed to their logical extreme. Scientists debate fiercely between these two ideas because each has strengths and weaknesses. Black holes are supported by a mountain of evidence. Astronomers have observed stars orbiting around invisible massive companions, moving so fast that the only possible explanation is the presence of a black hole. They have watched X-rays being emitted as gas falls into compact objects. They have detected gravitational waves from what appear to be the mergers of black holes. Most striking of all, in the year 2019, the Event Horizon Telescope collaboration unveiled the very first image of a black hole's shadow, captured at the heart of the galaxy M87. The dark circular silhouette with a glowing ring of hot gas around it matched exactly what general relativity predicts for a black hole. All of this evidence strongly supports the idea that black holes exist. On the other hand, gravastars are attractive because they solve some of the biggest puzzles that black holes create. The biggest of these puzzles is the information paradox. According to quantum physics, information can never be destroyed. But if black holes swallow everything that falls into them and hide it behind an event horizon, then information seems to be lost forever. Stephen Hawking famously showed in the 1970s that black holes emit radiation, now called Hawking radiation, and can eventually evaporate. But this process appears to erase information in a way that quantum theory forbids. Gravastars, by avoiding event horizons and singularities, might provide a way for information to remain accessible in some form. The exotic matter in the shell and the vacuum energy inside could make the laws of physics consistent once again. For this reason, gravastars are an elegant theoretical solution to problems that black holes cannot solve. The debate grows even more intense when one considers how hard it is to distinguish between black holes and gravastars by observation. Both would look like dark spheres surrounded by hot gas. Both would bend light around them, producing the so-called shadow captured by the Event Horizon telescope. Both would merge with partners to send out gravitational waves, yet subtle differences might exist. For example, the surface of a gravastar, being a real shell rather than an event horizon, might reflect some of the energy that falls on it. This could produce faint echoes in the gravitational waves, or tiny signals in electromagnetic radiation that black holes would not produce. Some researchers have looked for these echoes in the data from gravitational wave detectors like LIGO and Virgo. So far, the evidence is not conclusive, but the possibility remains open. If even one of these signals were detected, it could mean that what we thought were black holes are actually gravastars. It is also worth noting that gravastars, though elegant, face their own challenges. The idea requires exotic matter and vacuum energy arranged in very particular ways. Whether such structures can form naturally in the collapse of a star is not clear. The equations that describe gravastars work well on paper, but translating them into realistic astrophysical conditions is much harder. Nature may not provide the precise ingredients needed for their creation. Black holes, by contrast, are a natural outcome of stellar collapse according to Einstein's relativity, requiring no exotic substances. They are the straightforward, if frightening, prediction of gravity taken to its extreme. For many physicists, this makes them the more believable option. The story of black holes versus gravastars is not just about astronomy, but about the very foundations of physics. If black holes truly exist with singularities and horizons, then our understanding of space, time, and quantum mechanics is incomplete. If gravastars or some other alternative exists, then the universe may be more subtle than we think, hiding solutions to problems that currently baffle us. Either way, the debate pushes science forward. New observations, whether of shadows of supermassive objects or of the delicate ripples of space-time, may one day reveal which of these strange ideas is correct. Until then, the question remains open, and the cosmic contest between black holes and gravastars continues. The similarities between the two remain a constant source of confusion for observers. A black hole and a gravastar would both create accretion disks, rings of superheated matter spinning around them at incredible speeds. These disks would shine in X-rays and radio waves, flickering as clumps of gas spiral inward. Jets of particles could also shoot out from near their poles, powered by magnetic fields twisting around the swirling material. To a telescope on Earth, such jets would look the same whether they come from a black hole or a gravastar. Similarly, when two of these objects spiral toward each other, the gravitational waves they emit would have nearly identical patterns at first. Only in the final moments of merger might subtle differences emerge, like faint echoes or delayed signals. Detecting those differences requires instruments of extraordinary sensitivity, instruments that are only now reaching the needed precision. Another similarity lies in how both ideas challenge human imagination. Black holes already stretch the limits of understanding with their infinite densities and warping of time. Gravastars add a different kind of strangeness, replacing infinities with vacuum energy and shells of exotic matter. Both are reminders that the universe is far stranger than our everyday experience suggests. Both force physicists to ask deep questions about what space and time really are, what happens at the edges of knowledge, and whether reality might hold answers that seem absurd until proven true. In this way, even if gravastars do not turn out to exist, their very proposal has enriched the discussion and deepened the search for truth. One of the reasons scientists debate so strongly between black holes and gravastars is that the answer matters far beyond astronomy. If black holes exist as described in relativity, then at their heart lies a singularity, a place where the known laws of physics collapse. That would mean that our theories are incomplete and that new physics is waiting to be discovered. If gravastars exist instead, then they may point the way to uniting relativity with quantum mechanics, since they avoid singularities while still allowing strong gravity. This is why debates about these objects often spill into discussions of string theory, quantum gravity, and the nature of dark energy. They are not just questions about stars collapsing in space. They are questions about the deepest structure of reality. The cultural impact of this debate should also not be ignored. Black holes have captured the imagination of the public for decades. They appear in novels, films, and countless works of art. They are symbols of mystery and terror, of the unknown swallowing everything. Gravastars are newer and less well known, but as the idea spreads, they may capture imaginations in a different way. They are not monsters, but strange survivors, stars transformed into objects filled with the same mysterious energy that drives the universe's expansion. To think that such things might exist makes the cosmos even richer and more mysterious. When scientists gather at conferences or write papers debating black holes versus gravastars, the arguments are often technical, involving equations, simulations, and models of collapse. But beneath all of that lies something simple and human, the desire to know what is really out there. The universe has already surprised humanity countless times, from galaxies beyond the Milky Way to the expansion of space itself. It would not be shocking if the truth about black holes turned out to be stranger still, perhaps in the form of gravastars or some other exotic alternative. This sense of wonder drives the debate just as much as the data do. To draw the picture fully, one can imagine the life cycle of a massive star leading to these possibilities. A star many times heavier than our Sun burns brightly for millions of years. When its fuel runs out, it collapses. If relativity rules without modification, the result is a black hole, dark and final. If instead new physics intervenes, the collapse halts and a gravastar forms, strange and stable. In both cases, what remains is far beyond ordinary matter, far beyond human experience. The debate between black holes and gravastars is, in many ways, the story of modern physics itself. Bold ideas, fierce arguments, astonishing observations, and above all, the humility to admit that we still do not know all the answers. Black holes remain the leading candidate, supported by decades of evidence. Gravastars remain a daring alternative, offering solutions to deep puzzles. The similarities between them make the task of distinguishing them challenging. The differences between them make the stakes of the debate enormous. As telescopes sharpen their gaze and detectors grow more sensitive, the universe itself will have the final word on which of these strange possibilities is real. Until then, the conversation continues, a cosmic argument that is as much about the nature of reality as it is about stars and space. The hollow star concept is one of the strangest and most thought-provoking ideas in modern astrophysics. At its heart lies a vision of a cosmic object that looks on the outside like a star that has collapsed under its own weight, yet on the inside hides something utterly unexpected. Instead of being a solid, crushing ball of matter or a bottomless pit like a black hole, this object is hollow, its core replaced by a vast, empty-seeming void. Scientists call this type of hypothetical object a gravastar, short for gravitational vacuum star, and the thought of such a star challenges the way we usually think about the life and death of massive suns. To appreciate the hollow star idea, it helps to think first of what happens when a huge star runs out of fuel. In the normal story of astrophysics, when a star much larger than our Sun burns through its nuclear fuel, gravity takes over and squeezes it. If the star is heavy enough, nothing can stop this collapse, and the star shrinks into what we know as a black hole. Black holes have no surface in the usual sense. They have an event horizon, a one-way boundary beyond which nothing, not even light, can escape. Inside this horizon, matter is thought to be crushed into a point of infinite density, a singularity. This is the classic image that people know, a cosmic abyss that swallows everything. But the hollow star concept tells a different story. It suggests that, instead of falling into a singularity, matter might stop collapsing just before reaching that fate. At that point, something extraordinary happens. Space itself changes form, and the inside of the star is transformed into a region filled not with matter, but with a special kind of energy that behaves like the opposite of normal matter. This strange energy pushes outward instead of pulling inward. The result is that the middle of the star becomes hollow, like a bubble, and the outer layers form a thin, dense shell that traps the void inside. From the outside, such an object could look almost exactly like a black hole, but the inside would be nothing like it. The idea of a hollow star brings up images of a cosmic Russian doll. On the outside, a dark sphere that seems to hide a mystery, and on the inside, a bubble of emptiness that is not really empty but filled with something very exotic. The void-like interior of a gravastar is not a vacuum like the space between the stars. It is thought to be a vacuum of a different kind, one that is bubbling with what scientists call dark energy or vacuum energy. Dark energy is the same mysterious force that astronomers believe is making the universe expand faster and faster. In the hollow star, this energy holds open the bubble at the core, preventing the crushing collapse that would otherwise form a black hole. To picture this more simply, think of blowing up a balloon. The air inside pushes outward, while the skin of the balloon holds it in. A gravastar is like that balloon, but on a mind-bending scale. The thin outer shell of matter acts as the balloon's skin, while the interior is filled with a repulsive energy that pushes outward, keeping the shell from collapsing in. This balance creates stability where we would expect only doom. What makes this idea so fascinating is that it changes the story of stellar death into something far stranger. The hollow star would be an object where matter and energy meet in a delicate balance, creating a structure that is part star, part vacuum, and part mystery. If black holes are the monsters of the cosmos, pulling everything into a crushing singularity, then gravastars are like tricksters, pretending to be black holes but secretly hiding a bubble of nothingness in their hearts. The shell of a gravastar is another strange feature. Scientists describe it as being incredibly thin compared to the size of the whole object, but unimaginably dense. To give a sense of scale, the shell could be only a fraction of a millimeter thick, yet it would weigh as much as an entire star. This shell is where all the mass of the gravastar resides. The inside void does not add weight in the usual sense, since it is not made of ordinary matter. Instead, the shell is the anchor that holds the entire structure together, like a cosmic eggshell around a bubble of vacuum energy. Now, what would it be like inside such a hollow star? If you could somehow enter the gravastar without being destroyed, you would pass through the dense shell and find yourself in a region that seems empty, yet is far from ordinary. There would be no solid ground, no swirling gases, no blazing plasma like in a normal star. Instead, you would be surrounded by a strange, smooth nothingness that pushes outward with invisible pressure. Space itself would feel stretched and unnatural. Time would also behave differently, because the exotic energy in the void changes the way gravity and space-time interact. To an observer floating inside, the world might appear frozen, or distances might feel distorted. It would not be emptiness in the everyday sense. It would be more like stepping into a region of reality where the rules have been rewritten. The thought of a hollow star naturally leads to many questions. Could such objects really exist in the universe, or are they only mathematical possibilities? If they exist, how would we tell them apart from black holes, since from the outside both look almost identical? Scientists have tried to answer these questions by studying how light and matter behave near these objects. A black hole swallows everything beyond its horizon, but a gravastar might interact with its surroundings in subtler ways. For instance, when gas falls toward a black hole, it heats up and gives off radiation before crossing the horizon. In a gravastar, the presence of the shell and the strange void might change the pattern of this radiation. Detecting such differences could one day prove whether hollow stars are real. The concept of a hollow star also touches deep philosophical questions about the universe. If black holes are not the final fate of collapsed stars, and instead gravastars take their place, then the universe may be more diverse and surprising than we thought. The singularity of a black hole has always been a troubling idea, because it represents a breakdown of the laws of physics. By replacing the singularity with a bubble of vacuum energy, the hollow star concept offers a way to avoid that troubling infinity. In this sense, gravastars are not just strange stars, they are also attempts to heal the cracks in our theories of the cosmos. It is worth noting that the hollow interior of a gravastar is not a void in the sense of nothing at all, but more like a stage filled with invisible players. Quantum physics suggests that even the emptiest space is filled with fluctuations, tiny bursts of energy that pop in and out of existence. Inside a gravastar, these quantum effects could be magnified to cosmic proportions, turning the core into a seething sea of vacuum energy. This is why the gravastar's heart is sometimes described as a false vacuum, a state of space that is unstable compared to the normal vacuum we experience. The shell keeps this false vacuum contained, preventing it from spilling out into the rest of the universe. The scale of these objects is staggering. A gravastar formed from a star many times the size of the Sun could be only a few kilometers across, just like a black hole of similar mass. That means an object with the weight of several suns would be squeezed into a sphere no larger than a city. Within that tiny sphere lies the thin shell, holding in the hollow void. To imagine it in human terms, it would be like compressing the entire Earth into a ball the size of a marble and then hollowing out the inside. The density of the shell would be beyond anything we can imagine, far greater than even the core of a neutron star, which itself packs matter so tightly that a teaspoon would weigh billions of tons. The hollow star idea also sparks the imagination when we think about what might happen near its surface. If you are falling toward a black hole, once you cross the horizon, you are doomed. Nothing can escape. But with a gravastar, some theories suggest you might encounter the shell instead of vanishing into a singularity. Would you bounce off? Would you be absorbed and spread across the shell? Or would you pass through into the void and be lost in the strange vacuum inside? These questions show just how mysterious such objects remain. Some scientists have even suggested that the universe itself might resemble a kind of hollow star on the larger scale. Just as the interior of a gravastar is filled with vacuum energy that pushes outward, the cosmos we live in is expanding faster because of dark energy. This parallel makes the hollow star concept feel like a miniature model of the entire universe. In a sense, every gravastar could be seen as a tiny universe trapped inside a shell, mirroring the larger cosmos outside. The hollow star also connects to the human fascination with hidden spaces. Throughout history, people have imagined caves, chambers, and secret worlds hidden beneath the surface of the Earth. The gravastar is like the cosmic version of these myths, a star that looks solid and impenetrable, but that hides a hollow interior filled with a different reality. Instead of rock or fire, its hidden chamber contains the very fabric of space in a different state. One of the reasons scientists take the hollow star idea seriously is that it offers a possible answer to long-standing puzzles about black holes. For example, the so-called information paradox arises from the question of what happens to information that falls into a black hole. According to quantum physics, information should never be destroyed, but a black hole seems to erase it forever. A gravastar, with its shell and hollow core, might provide a way to store or release this information without breaking the rules of physics. The void inside could act as a kind of cosmic vault, where information is preserved in a form we do not yet understand. Exotic matter shells are one of the strangest and most puzzling ideas in modern astrophysics, and they are at the very heart of the theory of gravastars. A gravastar, short for gravitational vacuum star, is thought to be an alternative to black holes, where a black hole is described as a region of space where gravity has crushed matter down so tightly that nothing, not even light, can escape. A gravastar is built on a very different idea. Instead of being a bottomless pit of collapse, it is thought of as a bubble of space. Inside this bubble is not normal matter at all, but a strange form of vacuum energy, and surrounding it is a thin but incredibly powerful shell made of something that does not exist anywhere we can easily find or touch. This is what scientists call exotic matter. The shell of exotic matter is the key feature that holds the entire gravastar together, separating the eerie interior from the outside universe, and giving this hypothetical object its unique identity. Exotic matter is not the same as ordinary matter that makes up stars, planets, and people. Ordinary matter obeys familiar rules. It has positive mass, it pulls things toward it with gravity, and it resists being squeezed. Exotic matter, by contrast, is defined by its ability to break those rules. One of its most important qualities is that it can have negative pressure, or in some cases even negative energy density. That sounds impossible at first, but in physics it simply means that instead of pulling things in as gravity usually does, exotic matter can push outward. It is this pushing effect that makes exotic matter so valuable in theoretical models. For example, wormholes, which are shortcuts through space-time often described in science fiction, could only stay open if exotic matter lined their throats. In the same way, the Gravastar would only be stable if its outer layer consisted of exotic matter that pushes outward, perfectly balancing the inward pull of gravity from the material outside. The idea of the exotic matter shell is that it acts like a cosmic barrier. On one side of the shell lies the bizarre vacuum energy interior, a region where space itself is filled with a strange kind of energy that behaves differently from normal material. On the other side lies the rest of the universe, with stars, gas, dust, and radiation behaving as usual. Without the shell, the vacuum energy would not be able to remain in place. It would either expand uncontrollably, like the rapid inflation thought to have occurred in the earliest moments of the universe, or it would collapse inward. The exotic matter shell is therefore the balancing point, the firm but flexible skin of the Gravastar that keeps the whole structure intact. To understand why this shell is so mysterious, it helps to think about how unusual it is for physics to allow matter with negative pressure. In our daily experience, pressure is always positive. When you pump air into a tire, the air pushes outward against the rubber. When you press on a sponge, the sponge resists the squeezing. Negative pressure is the reverse. It is not something we can create with air or water or solids. But in cosmology, negative pressure has been suggested to exist in the form of dark energy, the invisible force that is believed to be pushing the universe to expand faster and faster. Exotic matter in the shell of a Gravastar would work in a similar way, but in a much more concentrated and extreme form. One way to describe the exotic shell is to think of it as a membrane with impossible strength. It is unimaginably thin compared to the size of the whole Gravastar, so thin that it could be smaller than the thickness of a human hair when scaled to cosmic dimensions. Yet within that tiny space it carries all the tension needed to resist collapse. If a Gravastar were the size of a star like our Sun, the shell would be only a few billionths of its radius in thickness. That means it is more like a sharp boundary line than a solid layer we can imagine. But this line of exotic matter is what separates reality inside from reality outside. The energy stored in this shell would also be vast beyond measure. Because the exotic matter has negative pressure, the shell acts almost like a spring under extreme compression, holding in an enormous amount of stress. The pressure inside could be so great that it is balanced only because of the counteracting negative properties of the exotic matter. If the shell ever failed, the Gravastar would instantly collapse, perhaps even turning into a black hole or exploding outward with unimaginable force. This makes the shell not only a stabilizer, but also the most dangerous and fragile part of the entire concept. Another fascinating feature of the exotic matter shell is the way it interacts with space-time. Ordinary matter bends space-time by curving it inward, like a ball resting on a stretched sheet. Exotic matter does the opposite. It bends space-time outward. In the case of the Gravastar, the exotic shell warps space in such a way that the strange vacuum interior does not spill out, while also preventing the Gravastar from developing the event horizon that defines a black hole. That means to an outside observer, a Gravastar might look almost identical to a black hole. It would be dark, compact, and exert intense gravitational pull, but it would lack the horizon beyond which no light escapes. Instead, the exotic shell would sit just outside the radius, where the black hole's event horizon would have formed, creating an object that mimics a black hole in appearance but is completely different in structure. This brings about one of the great mysteries of Gravastar shells. If they really exist, how would we tell them apart from black holes? Astronomers today look for black holes by observing the way light bends near them, the way stars orbit around them, or the bursts of radiation created when matter falls toward them. A Gravastar would produce almost the same signals. The exotic shell would not shine by itself. It would be as dark as the void inside. But it might reflect or scatter light in unusual ways, or it might create tiny echoes in gravitational waves that ripple out when two such objects collide. Detecting those tiny differences is one of the ways scientists hope to test whether Gravastars and their exotic shells might be real. The physics behind exotic shells is tied to general relativity, the great theory of gravity put forward by Albert Einstein in the early 20th century. In Einstein's equations, matter and energy determine how spacetime curves. Normally, the energy density is positive, and so space curves in one direction. But the equations also allow for negative values, at least in principle. Exotic matter shells are therefore not forbidden by mathematics, though they are extremely difficult to reconcile with known physics. In fact, quantum theory does predict tiny amounts of exotic behavior in certain situations, such as the Casimir effect, where two metal plates placed very close together in a vacuum experience a strange force due to quantum fluctuations. The Casimir effect creates negative energy density in a laboratory setting, though at scales far too small and weak to build anything like a gravastar. Still, it shows that the concept is not pure fantasy. When scientists describe exotic matter shells, they often use the language of balance and tension. The gravastar is thought to be a star that began collapsing under its own gravity, much like how a black hole forms. But instead of collapsing into a singularity, the process halted at the shell. The exotic matter formed a boundary at exactly the right radius, locking the vacuum interior in place and preventing further collapse. This is why the shell is sometimes compared to the crust of a neutron star, but far stranger. Neutron star crusts are made of dense atomic nuclei packed together like a metal lattice. Exotic shells, by contrast, are not made of protons, neutrons, or electrons at all, but of something beyond ordinary particle physics. It is worth noting that exotic matter shells raise many unanswered questions. For example, where would the exotic matter come from in the first place? Is it produced during the collapse of a massive star? Does it arise from quantum effects at the boundary of extreme gravity? Or is it a leftover ingredient from the early universe, present only in rare places where conditions are just right? None of these possibilities have been proven. The exotic shell remains a hypothesis, something that might or might not exist, but without it the Gravastar theory could not work. If exotic matter shells are real, their implications would be extraordinary. It would mean that the universe is capable of creating structures that are not only stranger than black holes, but perhaps more stable. A gravastar with its exotic shell would not contain a singularity, so it would not suffer from the paradoxes that plague black hole physics, such as the information loss problem. Instead, information about matter that falls into the gravastar might be preserved in the exotic shell, encoded somehow in its structure. This would make gravastars a possible solution to one of the deepest puzzles in theoretical physics. The shells also spark the imagination when it comes to cosmic engineering. Science fiction writers have sometimes speculated about advanced civilizations using exotic matter to build stable structures, perhaps even gravastars as sources of power. Because the exotic shell holds back vacuum energy, the object might serve as an energy reservoir, one that could be tapped in ways we cannot yet imagine. Though this is speculation, it shows how exotic matter shells, though only theoretical, push the boundaries of our thinking. Even in pure scientific terms, the exotic shell stands as an example of how extreme conditions force us to consider possibilities far beyond daily experience. Gravity near a collapsing star pushes matter to densities greater than anything we can create on Earth. In such environments, new faces of matter might appear, and exotic matter could be one of them. The fact that our equations allow it, and that its presence could explain phenomena otherwise attributed to black holes, keeps the idea alive. As research continues, astronomers search for subtle differences that might reveal the presence of exotic shells. For instance, gravitational waves from black hole mergers have been detected by instruments like LIGO and Virgo. If any of those signals show tiny echoes or deviations from what general relativity predicts for black holes, it could hint at the presence of a gravastar shell instead. So far, the data has not conclusively shown such differences, but the possibility remains open, and scientists are refining their tools to look closer. The exotic matter shell is more than just a barrier. It is the very essence of what makes a gravastar distinct from a black hole. Without it, the vacuum interior could not be held in, and the object would either collapse or disperse. With it, a new kind of astrophysical body could exist, one that mimics a black hole but avoids its deepest paradoxes. The shell is thin but mighty, strange but mathematically consistent, hypothetical yet tantalizing. It is the line between the ordinary and the extraordinary in the universe, the place where physics bends toward the impossible. When stars are born, they begin their lives as giant clouds of gas and dust. Gravity slowly pulls these clouds inward, squeezing hydrogen atoms until they start to fuse together. This nuclear fusion is what gives a star its light and heat. For billions of years, stars exist in a delicate balance. Gravity is always trying to pull everything inward, while the pressure from nuclear fusion pushes outward. As long as this balance is maintained, the star shines steadily. But when the fuel begins to run out, everything changes. The core starts to collapse, outer layers may be thrown away, and depending on the star's size, the end result can be a white dwarf, a neutron star, or a black hole. At least that is what standard astrophysics has taught us for many decades. Yet gravastars enter the story as a new alternative, another possibility for what might happen when gravity takes over and squeezes a star to its absolute limits. The formation of a gravastar is often described as a possible escape route from black holes. Normally, when a star many times heavier than the Sun runs out of fuel, the inward pull of gravity becomes unstoppable. The core collapses, and eventually a singularity is thought to form, a point of infinite density where space and time break down. Around it, an event horizon appears, a boundary from which nothing, not even light, can escape. This is the black hole. But some physicists began to wonder, is this really the only possible outcome? Must stars always create singularities? Perhaps there is another way the collapse could settle, creating an object that looks very much like a black hole from the outside but is very different on the inside. That is where the gravastar enters. To understand this strange alternative, one has to picture the collapse of a star in its final stages. Imagine a massive star that has burned through all of its fuel. Its core begins to shrink at an incredible pace. Pressures become unimaginable, trillions upon trillions of times greater than what we experience on Earth. Temperatures soar, particles are squeezed together, and matter is crushed almost beyond recognition. But instead of reaching the singularity stage, some scientists have proposed that a strange phase change might take place. Much like how water can suddenly turn into ice or steam depending on conditions, the collapsing core could undergo a transformation of its own. Instead of becoming infinitely dense, the matter inside the star might transform into something entirely new, a region of vacuum energy, sometimes called dark energy, which has a repulsive effect on space. In this scenario, the collapse does not go all the way to a singularity. Instead, it stops at the threshold and produces a new structure. At the very center of the gravastar would not matter at all, but this strange vacuum energy, pushing outward with incredible strength. Surrounding this vacuum bubble would be a thin but extremely strong shell of exotic matter, the likes of which we do not fully understand but which would serve as a kind of membrane holding everything together. This shell would balance the push from the vacuum energy inside with the pull of gravity outside. The result would be a stable, compact object that looks like a black hole to anyone observing it from afar, but does not contain an event horizon or a singularity. The pathways to forming such an object are still hypothetical, but the most likely route begins with the collapse of very massive stars. When a star many times heavier than our Sun dies, the collapse can be so extreme that the laws of physics as we know them might not be enough to describe what happens. Traditional black hole theory assumes that gravity wins completely, crushing matter into nothing but a point. But gravastar theory suggests that at a certain density the rules change. Instead of continuing the collapse, the star's core transitions into this exotic state, forming a bubble of vacuum energy. This would require conditions that are so extreme that no laboratory could ever reproduce them. Yet the universe naturally provides such laboratories in the form of collapsing stars. One can imagine the process unfolding in stages. First, the star lives its long, bright life, burning fuel steadily. Then, as billions of years pass, the fuel begins to run low. Fusion slows, the outward pressure weakens and gravity begins to take control. The core shrinks rapidly, crushing atoms closer and closer together. At this point, if the star is small, it will end as a white dwarf, and if it is medium-sized, it may end as a neutron star. But if the star is very massive, the pressure will be too great, and the collapse will continue beyond these states. Instead of forming a black hole, though, something unusual might happen. A sudden change in the fabric of space and energy could occur, and the core could reorganize itself into this strange configuration we call a gravastar. Scientists have speculated about what might trigger this transition. One idea is that quantum effects, tiny processes happening at the smallest scales, might step in to prevent the formation of a singularity. In normal black hole theory, Nothing can stop the collapse once it starts, but quantum mechanics suggests there may be limits to how dense matter can become. The Gravastar model takes advantage of this possibility. Rather than letting the collapse go all the way to infinity, it suggests that quantum processes create a sort of quantum pressure or vacuum bubble that resists further collapse. This would be like the universe finding a loophole in its own rules, stopping the collapse just before a singularity forms and settling into a new stable state. Another possible pathway involves the behavior of dark energy. In the wider universe, dark energy is thought to be driving the expansion of space itself. If a collapsing star could somehow trap a pocket of dark energy inside its core, that energy might resist collapse and create a repulsive force. The outer layers of the star would then be held back by the vacuum energy inside, while the exotic matter shell stabilizes the structure. This balance of forces is very delicate, but if it works, the Gravastar could exist indefinitely, neither collapsing further nor exploding outward. From the outside, a Gravastar would be nearly impossible to distinguish from a black hole. Both would have extremely strong gravitational pulls, bending light around them, warping time, and swallowing anything that ventured too close. Both would appear as dark voids surrounded by glowing material if gas or dust fell in. But deep inside, they would be utterly different. Instead of a singularity hidden behind an event horizon, the Gravastar would have a strange vacuum bubble and a thin shell of exotic matter. The idea that Gravastars might form through stellar collapse also raises questions about how common they could be in the universe. If every massive star ended as a black hole, then Gravastars would be rare. But if there are conditions where the collapse naturally favours the Gravastar pathway, then there could be many of them hidden among the population of black holes we think we see. Astronomers are still trying to determine whether any of the black hole candidates detected so far might actually be Gravastars in disguise. To make the idea more vivid, one can picture a massive star nearing the end of its life. For millions of years it has burned brightly, fusing hydrogen into helium, then helium into heavier elements. Its core grows hotter and denser with each passing stage. When it finally runs out of fuel, the collapse begins. In seconds, the core shrinks, crushing protons and electrons into neutrons. If the star is large enough, this is still not enough to stop gravity, and the collapse continues. The density rises to levels where normal matter cannot survive. But instead of collapsing into a singularity, the core undergoes a strange transformation. Space itself changes. A bubble of vacuum energy appears, pushing outward with enormous force. A shell of exotic matter forms around it, locking the structure in place. The star has not created a black hole, but something just as mysterious, a Gravastar. The possible formation of Gravastars is not only fascinating but also deeply unsettling, because it forces us to rethink the very endgame of gravity. Black holes have long been the champions of extreme gravity, the objects that mark the ultimate victory of collapse. But Gravastars suggest there might be another outcome, one where the universe avoids the paradoxes of singularities and event horizons by replacing them with a different, equally exotic structure. If Gravastars do form in this way, then every black hole we have ever observed could secretly be something else. We might be staring at Gravastars without realizing it, mistaking them for black holes because from a distance they look the same. Only the subtle details of how they interact with their surroundings might reveal their true nature. For example, the way they swallow matter, or the way they emit radiation, might carry clues. Some scientists have even suggested that the ripples in space-time caused by collisions, gravitational waves, could hold the key to telling them apart. The observational challenges are so overwhelming that the scientific community still debates whether we will ever be able to know if these strange objects are really out there or if black holes remain the only explanation. The difficulty begins with the fact that black holes themselves are already very hard to observe directly. A black hole does not emit light, does not shine, and does not reflect radiation in the way that stars or planets do. Everything we know about them comes from indirect evidence: how they affect nearby stars, how they bend light through gravitational lensing, how matter heats up when it falls toward them, and how gravitational waves ripple through the cosmos when they merge. Gravastars, if they exist, would produce almost identical signs in all of these situations. If one looked at the sky through a telescope, even the most advanced one, a Gravastar sitting quietly in space would appear no different from a black hole of the same mass. The light around it would curve the same way, the gravitational pull would be nearly identical, and unless some small difference is detected, the two objects would be indistinguishable. Another problem lies in the fact that the difference between black holes and gravastars only shows up very close to their surfaces. For a black hole, that surface is the event horizon, an invisible boundary beyond which nothing escapes. For a gravastar, there is no event horizon, but instead there is a thin shell of exotic matter. To notice the difference, one would need to see extremely fine details of how light, radiation or particles behave right at the edge. But that edge is unimaginably far away, often tens of thousands to millions of light years from Earth, and any signals we receive are blurred by distance, dust, and interference. Even the Event Horizon Telescope, which in the year 2019 gave us the first image of a black hole in the galaxy, Messier 87, did not truly photograph the event horizon itself, but rather the bright glowing gas swirling around it. Such data cannot yet separate the subtle features that would reveal whether the central dark spot is a black hole or a gravastar. One might think gravitational waves could provide the answer. When two compact objects like black holes spiral into each other and merge, they create ripples in space-time that detectors like LIGO and Virgo can pick up. The pattern of those waves encodes information about the nature of the objects involved. In theory, if two gravastars collided, the signal might have a slightly different afterring compared to black holes. Black hole mergers produce a so-called ringdown, a fading vibration as the newly formed hole settles into a stable shape. Gravastars might produce echoes instead, as the waves bounce inside the exotic shell before escaping. These echoes would be very faint, arriving after the main signal, and could in principle serve as a fingerprint. But the difficulty is that gravitational wave detectors are noisy, filled with random fluctuations from the Earth and from the instruments themselves. Extracting a faint echo from that sea of noise is like trying to hear the faint sound of a single raindrop in the middle of a thunderstorm. Some researchers claim to have seen hints of such echoes, but others argue that these are statistical illusions. Until detectors improve to a much higher sensitivity, we cannot say for sure. Another observational challenge comes from the way matter behaves when it falls toward these objects. Around black holes, infalling matter forms an accretion disk, heating up to millions of degrees and emitting X-rays. Gravastars would also pull matter in, and the disk would shine in a nearly identical way. One possible difference might arise if matter strikes the solid shell of a gravastar rather than disappearing beyond an event horizon. If this happened, one could expect a sudden burst of radiation, a flash revealing that the object has a surface. But the shell of a gravastar, if it exists, might absorb or scatter this energy in ways that mimic the disappearance into a horizon. Even if flashes occur, they may be too weak or too rare to be noticed from Earth. We would need to monitor countless objects over long periods of time with extremely sensitive instruments, and even then the signals could be confused with other cosmic phenomena such as pulsars, magnetars, or supernova remnants. There is also the difficulty of scale. The objects we are studying are unimaginably large and far away. A stellar mass black hole, formed from a collapsing star, may be only a few tens of kilometers across, yet it could lie thousands of light years from us. A supermassive black hole, like the one in the center of our Milky Way galaxy, stretches across millions of kilometers, but it is over 25,000 light years away. At such distances, even the most powerful telescopes reduce these cosmic giants to tiny specks of data. The subtle differences between a gravastar and a black hole could be smaller than the margin of error in our instruments. It is like trying to tell whether a coin on the surface of the moon is heads or tails using a pair of binoculars. The technology simply is not sharp enough. Another issue is that the mathematics describing gravastars is itself uncertain. Different versions of the theory predict different observable effects. Some models suggest strong echoes in gravitational waves, while others predict almost none. Some suggest bright flares when matter hits the shell, while others say the shell would reflect energy inward, making the object appear just as dark as a black hole. Without a consistent prediction, astronomers do not even know exactly what to look for. If one team searches for echoes but another version of the theory says echoes should not exist, then even a null result proves nothing. This uncertainty in the theory makes observational testing extremely challenging. Cosmic background noise adds another layer of difficulty. The universe is full of radiation, particles, and random events that complicate measurements. Gamma-ray bursts, X-ray flashes, quasars, and countless other energetic phenomena fill the sky with signals that can mask the faint signs we need to distinguish a gravastar from a black hole. Gravitational lensing, for example, bends light around massive objects, but galaxies and dark matter also bend light, mixing their effects with those of the compact object itself. This makes it extremely hard to isolate the unique fingerprint of a gravastar. Even if we manage to approach closer in our measurements, quantum effects create more confusion. Black holes are thought to emit Hawking radiation, an incredibly faint glow that slowly causes them to evaporate over trillions of years. Gravastars, on the other hand, may not produce this radiation, or may release it in different ways. But Hawking radiation is so weak that no telescope on Earth or in space has ever detected it, and we are unlikely to do so anytime soon. The difference, therefore, remains invisible. Another subtlety lies in time dilation. Near a black hole, time slows down for an outside observer watching matter fall in. To us, the infalling material appears to freeze near the event horizon, never quite crossing it. For a gravastar, the shell may produce a similar effect, with time dilation causing matter to appear stuck near the surface. In either case, from our viewpoint on Earth, the two scenarios would look almost identical. The only way to tell the difference would be to detect radiation emitted from the final impact, but as explained earlier, this is far from easy. We also face limitations in building simulations. To predict how a gravastar should look, scientists use supercomputers to solve Einstein's equations for these exotic objects, but the equations are so complex that they can only be approximated, and small differences in assumptions produce very different outcomes. When comparing those results with telescope data, the uncertainties are so large that one cannot claim a firm distinction. It is like comparing two blurry sketches with a blurry photograph and trying to decide which one matches. Future instruments may help. Projects like the Laser Interferometer Space Antenna, planned for the next decade, could detect gravitational waves from sources across the entire universe with far greater precision. Extremely large telescopes, being built in Chile and other locations, may capture finer details of accretion disks and shadows of compact objects. Space-based X-ray observatories might detect subtle variations in bursts and flares. With these tools, the hope is that scientists might catch the one key signature that betrays a gravastar. But until then, the challenge remains almost insurmountable. It is also worth remembering that nature may not cooperate. Even if gravastars exist, they may behave so much like black holes that no observational difference is ever detectable. In such a case, the distinction would remain purely theoretical, a matter of equations and philosophy, rather than measurable science. Some physicists even argue that if gravastars and black holes cannot be told apart by any experiment, then they are effectively the same object, at least from the standpoint of observation. This raises deep questions about the nature of science. Is something real only if it can be measured, or does it exist if mathematics allows it? Still, the search continues, driven by curiosity. Each new observation of a black hole candidate becomes an opportunity to test whether the universe is hiding gravastars in plain sight. The black hole at the centre of our galaxy, Sagittarius A, is under intense scrutiny. Astronomers are examining its flares, its orbits of nearby stars, and its radio emissions for any irregularities. Some claim tiny deviations might hint at a surface instead of a horizon, but none of these claims are confirmed. Similarly, the study of mergers by gravitational wave detectors continues, with researchers reanalyzing every dataset for faint echoes. So far, the evidence leans toward black holes, but the door for gravastars is not yet closed. The mystery of distinguishing gravastars from black holes is not only about technology, but also about human perception. Our senses evolved to handle the middle-sized world of Earth, trees, rivers, mountains, and skies. To deal with the extremes of the cosmos, we rely on machines, equations, and indirect reasoning. Gravastars challenge us to stretch those tools to their absolute limits. They sit on the razor's edge between the known and the speculative, between what we can measure and what we can only imagine. The observational challenges, therefore, are immense. Gravastars and black holes cast the same shadows, bend light in the same way, pull on stars with the same force, and swallow matter with the same hunger. Their differences lie hidden in tiny details that our instruments barely graze. To distinguish them requires not only better telescopes and detectors, but also sharper theories and more patient analysis. Perhaps in the future, with space-based interferometers and next-generation observatories, we will finally catch a glimpse of the difference. Gravitational waves are one of the most extraordinary discoveries in the history of science. They are ripples in the very fabric of space and time, created when some of the most violent and energetic events in the universe take place. When black holes crash into each other, when neutron stars spiral together, or when colossal explosions shake dying stars, these waves travel across the cosmos, stretching and squeezing space itself. For a long time, their existence was only a prediction of Albert Einstein's general theory of relativity, proposed in the year 1915. But in the year 2015, humanity finally detected them directly for the first time, a century after they were predicted. That historic moment proved that space and time can indeed ripple like the surface of water, and that we have the ability to listen to the universe in a completely new way. Ever since that breakthrough, scientists have been developing increasingly sensitive detectors to capture more of these whispers from space. Current detectors like LIGO in the United States, Virgo in Italy, and Kagra in Japan have already given us dozens of gravitational wave detections, most of them from merging black holes and neutron stars. But even though these instruments are incredible achievements, they are still just the beginning. They can only detect waves in certain frequency ranges, and they are sensitive enough to catch events that happened within a certain distance of Earth, but not beyond that. There is an entire hidden universe of gravitational wave signals that remains invisible to us, simply because our current technology cannot reach them. That is why the future of gravitational wave astronomy is so exciting. New detectors, more advanced than anything we have now, may reveal signs of things we cannot yet imagine. One of the most intriguing possibilities is that these future detectors might reveal signals not just from black holes or neutron stars, but from completely new kinds of objects such as gravastars. A gravastar, short for gravitational vacuum star, is a theoretical alternative to a black hole. Instead of collapsing into a singularity surrounded by an event horizon, as black holes are thought to do, a gravastar would be a strange, hollow object. At its core, instead of matter, it would contain a bubble of dark energy or vacuum energy, pushing outward, while the outside would be held together by a shell of exotic matter with unusual properties. To an observer from far away, a gravastar might look almost exactly like a black hole, but its interior would be radically different. This raises an important question. Could gravitational waves carry the fingerprints of such exotic objects? Could the ripples in space-time tell us whether we are looking at a black hole or at something even stranger? The answer may lie in the fine details of the signals we collect. When two black holes collide and merge, the gravitational waves they send out follow a very precise pattern. The first stage is the inspiral, when the two objects orbit closer and closer, losing energy through radiation. Then comes the merger, when they crash together. Finally, there is the ringdown, when the newly formed object settles into a stable state, like a struck bell slowly quieting down. If the final object is a black hole, its ringdown has a very specific mathematical shape, described by the equations of general relativity. But if the final object were a gravastar or something else, the ringdown might look slightly different. Future detectors, with more sensitivity, could potentially pick up on these subtle differences. They might notice extra echoes in the signal, little reverberations of space-time bouncing back and forth inside the exotic matter shell of a gravastar, or signs that the waves die away in a different way than expected. This idea of echoes in gravitational waves has already been explored in theory. A black hole has an event horizon, a point of no return where nothing, not even light, can escape. Because of that, waves simply fall inside and are lost forever. But a gravastar has no event horizon. Its outer shell might reflect or trap some of the waves, sending them back out again in faint secondary signals. Detecting these echoes would be one of the strongest pieces of evidence that something other than a black hole exists in the universe. However, the echoes would be extremely faint, buried deep in the noise of the data. Current detectors are not quite sensitive enough to confirm them, though some researchers claim to have seen hints. This is where the future comes in. The next generation of detectors, such as the Einstein Telescope in Europe or the Cosmic Explorer in the United States, both planned for the coming decades, will be much more powerful. They will be able to measure gravitational waves with 10 times the sensitivity of current instruments, opening a window to these delicate features. Even more revolutionary will be space-based detectors like LISA, the Laser Interferometer Space Antenna, planned by the European Space Agency for launch in the year 2035. Unlike ground-based detectors, which are limited by Earth size and by seismic noise from the planet itself, LISA will place 3 spacecraft millions of kilometers apart in space, linked by laser beams. This enormous scale will allow it to detect gravitational waves at much lower frequencies than ground-based observatories. Those low-frequency waves come from different kinds of cosmic events, such as supermassive black holes merging at the centers of galaxies, or possibly from exotic objects like Gravastars if they exist on such large scales. With LISA, scientists hope to listen to the deep, slow rumblings of the universe that are completely hidden from us today. The question then becomes, what kinds of signs should we look for in these future detectors to know whether we are seeing a black hole or something stranger? One possibility is the exact frequency spectrum of the waves. Black holes obey very strict rules called quasi-normal modes in their ring-down stage, with frequencies and decay times determined only by their mass and spin. If the observed signal does not match these rules perfectly, it could mean we're not dealing with a black hole. A Gravastar with its shell and vacuum interior would likely produce additional modes, slightly shifting the frequencies or adding new peaks. In practice, detecting these differences requires detectors with not only high sensitivity, but also long observation times, since the more data we have, the better we can extract faint features from the noise. Another possible sign is in the inspiral stage, before the merger. As two objects orbit each other, their gravitational pull depends on their structure. Black holes are bald in the sense that they have no extra features beyond mass and spin, but Gravastars might deform differently, changing the way they radiate energy. This could alter the phase of the inspiral signal in subtle ways. If future detectors can track the inspiral for long enough with great precision, they may be able to notice these deviations. In other words, by listening carefully to the rhythm of the spiraling dance, we might tell whether the dancers are black holes or Gravastars in disguise. Beyond Gravastars, gravitational waves may reveal other exotic possibilities. Some scientists have suggested objects like boson stars, made entirely of hypothetical particles called bosons, or wormholes, which are tunnels through space-time. Each of these strange objects would leave its own mark in the gravitational wave signal, often in the form of echoes, unusual ring-downs, or distorted inspirals. The future detectors will not only confirm more black holes and neutron stars, but may also act as hunters for these exotic objects. If even one convincing detection of such a signature were made, it would revolutionize our understanding of physics, showing us that the universe contains entities beyond the black holes and neutron stars we know. Of course, detecting these signs will not be easy. The universe is noisy, and gravitational wave signals are often incredibly weak by the time they reach Earth. To detect them, scientists use advanced techniques of data analysis, filtering out background noise and enhancing the signals. The search for echoes or other exotic features requires even more sophistication, since the signals are expected to be faint and ambiguous. That is why improvements in detector technology must be matched with improvements in computing power and analysis methods. Machine learning, artificial intelligence, and better models of how exotic objects behave will all play a role in making sense of the data. The excitement lies in the fact that gravitational waves offer a new kind of evidence different from light. Traditional astronomy relies on photons, whether visible light, radio waves, or X-rays, but these can be absorbed, scattered, or hidden by matter. Gravitational waves, on the other hand, pass through matter almost undisturbed, carrying clean information about the most extreme events in the universe. They give us a direct line to phenomena that would otherwise remain invisible. If Gravastars or other exotic objects exist, they may not be visible through telescopes, but their fingerprints in gravitational waves might give them away. Looking forward, the timeline of progress is already set. The current generation of detectors will continue to improve over the next decade, with upgrades increasing their sensitivity. By the early 2030s, the Einstein Telescope and Cosmic Explorer may be built, ushering in a new era of ground-based observations. In the mid-2030s, LISA will take to space, expanding the range of frequencies we can hear. With these instruments combined, scientists will have a network of ears listening to the cosmos across a vast spectrum, from the rapid high-pitched chirps of stellar black holes to the deep bass of supermassive ones. Somewhere in that orchestra of cosmic sounds, the subtle notes of gravastars may finally be heard. If such a discovery were made, the implications would be enormous. It would challenge our understanding of gravity, quantum physics, and the ultimate fate of collapsing stars. It would show that nature has more tricks than we imagined, and that the story of extreme gravity is not limited to black holes. Perhaps gravastars are rare, or perhaps they are common but have always been mistaken for black holes. Only the gravitational waves can tell us. The future detectors, with their heightened sensitivity, longer baselines, and broader frequency coverage, will act like magnifying glasses for these cosmic mysteries. They will allow us to go beyond the shadowy outlines of black holes and peer into the deeper truths of space-time. The universe is vast, and we have only just begun to hear its gravitational symphony. Each new detector is like adding another instrument to the orchestra, sharpening the sound and expanding the range. With every detection, we learn more about how stars die, how galaxies grow, and how exotic matter might exist. In the decades to come, the dream is that gravitational waves will not only confirm Einstein's theories again and again, but will also reveal where those theories break down, pointing the way toward new physics. Signs of gravastars, echoes of exotic structures, or whispers of unknown particles may all lie hidden in the cosmic ripples, waiting for the day when our ears are sharp enough to hear them. The danger of extreme gravity deals with what happens when matter and light themselves are exposed to conditions that go beyond anything we normally experience in the universe. To understand the danger of such a thing, we must picture what it would be like to come close to a gravastar, a strange object that some scientists believe might exist as an alternative to black holes. A gravastar is short for gravitational vacuum star. It is not like an ordinary star that shines by burning nuclear fuel in its core. Instead, it is thought to be made of a hollow interior filled with an exotic type of energy, surrounded by a very thin but extremely dense shell of matter. This strange shell could be made of material that behaves in ways we cannot normally imagine, able to resist collapse and trap the strange energy inside. Outside, the gravastar's pull would be almost identical to that of a black hole, because its mass would be squeezed into such a small space that it bends space and time around it to an extreme degree. Now imagine approaching such a thing. The danger begins long before you even reach the surface or the edge. Gravity that's strong does not act gently. It pulls differently on the parts of you that are closer compared to the parts that are farther away. This effect is often called tidal forces, but in extreme gravity it would not feel like the mild pull of tides on Earth. Instead, if you were a person drifting toward a gravastar, the side of your body closer to it would be yanked more strongly than the side farther away. Your legs might be pulled downward while your chest and head lagged behind. The difference in force would stretch you out like a long thread. Scientists sometimes call this process spaghettification, because your body would be pulled into a long, thin shape like a piece of pasta. Even atoms themselves would not be safe from this stretching, because the difference in gravitational pull would grow so strong that it could rip apart the bonds that hold matter together. The particles that make up atoms might themselves be torn from one another if you came close enough. But the story does not end with just being stretched. The deeper danger is that light itself, the fastest thing in the universe, cannot easily escape such a pull. Around a gravastar there would exist a region where light is trapped in circles, unable to escape outward but also not falling inward. This is sometimes called the photon sphere, a place where beams of light could orbit the object endlessly. If you were looking at a gravastar, you might see distorted and repeated images of the same stars behind it, bent around in strange rings and arcs, as if the sky itself had been twisted into knots. Light from your own flashlight, if you tried to shine it toward the object, might curve around and come back toward you, making it seem as though the darkness itself was playing tricks with your eyes. The danger here is that you could not trust your senses, because light no longer travels in straight lines the way it does in ordinary space. The pull on time itself would also become terrifying. Near a gravastar, time for you would slow down compared to someone far away. Imagine that you had a friend waiting at a safe distance while you moved closer. From your own point of view, perhaps only a few minutes might pass as you drifted near the shell of the Gravastar. But to your friend far away, hours, days, or even years could slip by while they watched you move slower and slower, never seeming to actually reach the edge. To them, you would appear to freeze, trapped at the boundary, fading into darkness. Yet for you, the passage of time would feel normal until you reached a point where the forces destroyed you. This stretching of time, called time dilation, is not just a trick of the mind. It is real, caused by how gravity bends space and time itself. Matter near a Gravastar also faces strange dangers. If gas, dust, or even entire stars wandered too close, they would be shredded into thin streams by tidal forces. These streams would swirl around the Gravastar, forming what scientists call an accretion disk. Such a disk glows with unbelievable brightness, because as the matter falls inward, it is squeezed and heated until it gives off enormous amounts of light and energy. The glow of such a disk could outshine entire galaxies, making the Gravastar look like a blazing beacon in the darkness of space. Yet no matter how bright the disk, the inside remains invisible, because the extreme gravity bends and swallows the light before it can escape. If a spaceship ever tried to fly close, it would be roasted by radiation from the disk long before it could even touch the shell itself. Radiation is another danger, because near such strong gravity, particles move at nearly the speed of light, colliding and releasing high-energy rays. These rays, like X-rays and gamma rays, can destroy the molecules of life, tearing apart DNA and breaking chemical bonds. For a living creature, such radiation would be deadly in seconds. Even machines would not last long, because the electronics would be fried by the constant bombardment. The environment around a Gravastar would therefore be not only gravitationally dangerous, but also poisoned with lethal energy. The strangest part of a Gravastar is its shell. Unlike a black hole, which hides everything behind an event horizon, a Gravastar might have a physical surface where matter hits and interacts. If you could somehow survive the tidal stretching and the radiation long enough to strike the shell, you would not land gently. The speed at which you would be pulled in means you would slam into the surface at nearly the speed of light. The impact would release more energy than an atomic bomb, but concentrated into the size of your body. You would be instantly vaporized, and the shell itself might quake from the force of the collision, sending out ripples of energy across space. This makes the Gravastar not just a passive object, but an active one, able to react violently when struck by matter. Light that tries to leave the Gravastar's surface faces another cruel fate. Because of the extreme warping of space and time, light emitted outward loses energy as it climbs away from the strong gravitational field. To someone watching from a safe distance, the light would appear redder and dimmer, stretched into longer and weaker wavelengths. This process is called gravitational redshift. If you stood at the shell and tried to shine a bright lamp upward, by the time the light reached someone far away, it might appear as only a faint glow, almost invisible. In fact, if the shell is strong enough, nearly all light trying to escape could be redshifted into nothingness, making the object look as dark as a black hole, even though it has a surface. The extreme gravity of a Gravastar would also play havoc with orbits of nearby objects. A planet wandering too close might have its path twisted so violently that it spirals inward to destruction. A star in orbit might be slowly robbed of its gas, feeding the glowing disk. Even entire clusters of stars could be disturbed, flung out of their galaxies or drawn inward to fuel the beast. Over millions of years, a Gravastar could carve up its surroundings, leaving behind only chaos and darkness. Galaxies with such objects at their centers might show violent jets of energy shooting out for thousands of light years, powered by the feeding frenzy of matter being torn apart and devoured. If you think about what this means for light, it is even more chilling. Light, which normally sets the cosmic speed limit, is bent, slowed, and in many cases completely trapped. Imagine standing near a Gravastar and trying to send a message with a laser beam. The beam would bend back, curve into orbits, or vanish into the shell. Communication itself would become impossible near such a monster, because signals could not travel in straight paths. You could shout into the void with the brightest light, and no one would ever see it. It is as if the Gravastar erases not only matter, but also the very possibility of sharing information. And yet, for all this danger, Gravastars also hold a strange beauty. The way light bends around them can create patterns called Einstein rings. where the image of a star or galaxy behind the Gravastar is warped into a glowing circle. A single object can appear many times, duplicated and stretched by the curved space around it. To an observer, this would look like a hall of mirrors written across the sky. Such beauty is deadly, however, because to witness it closely means to be too near to escape. The danger is not limited to individuals or small objects. If a Gravastar sat in the centre of a galaxy, as scientists believe black holes do, it could shape the fate of billions of stars. The galaxy's spiral arms might be influenced by its pull, and the rhythm of star birth and death could be tied to the energy released as matter falls in. In this way, the Gravastar becomes not only a destroyer, but also a cosmic architect, shaping the grand design of galaxies through its hunger and its gravity. The thought of being near such an object is almost unbearable. For us on Earth, gravity feels gentle. It holds our feet to the ground and keeps the moon in orbit. But the gravity of a Gravastar is not gentle at all. It is a force that can stretch space itself, slow time, crush matter, bend light, and poison everything with deadly radiation. It is a reminder that the universe is not built only for comfort. It has places where the laws of physics push to their most terrifying limits, and where survival is not possible. Yet scientists still wonder whether Gravastars might exist, because they could explain some mysteries that black holes cannot. If they do, then somewhere out there are objects with shells of exotic matter, filled with a vacuum energy that pushes outward while gravity pulls inward, balanced in a fragile dance. They would be objects that look to us like black holes from far away, but are in fact stranger still. To come close to one would be to step into a place where the normal rules of space and time collapse, where matter and light face dangers they cannot overcome, and where the universe reveals just how extreme its creations can be. The danger of extreme gravity, especially near a Gravastar, is not simply a matter of being pulled in. It is the loss of identity of matter itself, the destruction of information carried by light, the collapse of time into strange rhythms, and the transformation of order into chaos. It is both fascinating and horrifying to imagine. A Gravastar may be a hollow shell filled with vacuum energy, but the dangers it presents are as solid and deadly as any nightmare the cosmos can conjure. Cosmic traps for spacecraft are among the greatest nightmares that humankind could face in its daring journey into the vastness of the universe. When people dream of exploring other planets, crossing the dark oceans of interstellar space, or sending missions to the very edges of the galaxy, they often imagine the dangers of hostile environments, radiation storms, or mechanical failure. Yet, the true danger, the one that lies hidden in silence, is not simply what can break a machine, but what can completely erase it from existence. These traps are made not by enemies or by chance, but by the laws of nature themselves, waiting in the dark like invisible snares. The universe is beautiful, but it is also merciless, and the traps it has set for spacecraft are proof that nature can both inspire and terrify. A spacecraft travelling through space may face many regions where the rules of gravity and energy combine into something so powerful and strange that escape becomes nearly impossible. These are the cosmic traps, places where matter, light, and even time itself can become tangled. A ship that strays too near can find itself stretched, twisted, and swallowed, without leaving the smallest trace behind. To human imagination, these regions are like black whirlpools in a cosmic ocean, pulling everything down into their silent depths. Unlike whirlpools of water, which can be seen, measured, and avoided, cosmic traps are often invisible. They announce their presence not by their own shape, but by what they do to the world around them. A star that circles too closely, a cloud of gas that glows brighter as it falls, a strange bending of light from a distant galaxy. All these signs whisper of a trap lurking unseen. The most famous of these cosmic traps are black holes, but they are not alone. The universe may hide other strange structures, like Gravastars or wormholes that have collapsed into deadly pits. Whatever their nature, the principle is the same. They are regions where gravity grows so overwhelming that even light, which is the fastest traveller in the universe, cannot escape. A spacecraft that drifts too close will discover that ordinary engines are useless no matter how powerful. The closer it gets, the more the very fabric of space and time seems to betray it. Distances stretch, time slows, and directions lose meaning. For the crew inside, it would feel like being caught in quicksand made not of earth or mud, but of reality itself. Imagine a future spacecraft, long and sleek, its silver body gleaming as it sails between the stars. Its engines burn quietly, pushing it forward at a steady pace. The crew inside is busy with routine tasks, charting their course, checking the instruments, recording the faint signals of distant worlds. Around them stretches an endless ocean of stars, glittering like jewels. Then, slowly, the readings begin to shift. Gravity detectors start to register a pull that should not be there. At first, it is too small to notice, no more than a whisper in the data. But over hours and then days, the numbers climb. Something massive is nearby, something invisible. The ship's cameras sweep the region, yet there is nothing. No star, no planet, no glowing nebula, just empty space. And still, the pull grows stronger. The crew does not yet realize that they are approaching a cosmic trap. Their instruments will give hints, but the trap itself hides its body behind a cloak of darkness. The only evidence may be strange distortions of starlight ahead. Points of light curve and bend as though seen through rippling water. This bending is gravity's handwriting, the sign that an object of immense weight lurks there. If the crew does not change course soon enough, the ship will cross a point of no return. Past this invisible line, escape is impossible. Engines could roar with all their strength, yet the ship would still fall inward, drawn deeper and deeper into the dark heart of the trap. The nightmare of such a moment is not only in the knowledge that escape is gone, but also in the way the fall takes place. To those far away, watching from safety, the ship would appear to slow down as it approached the edge, stretching into a faint shadow that freezes in place, never quite crossing the boundary. To them, time would seem to stop for the doomed explorers. But for the crew inside, time continues. They would feel the acceleration, the stretching, the endless dive inward. The light outside their windows would grow stranger. Stars would smear into arcs, colours would shift, and darkness would creep in from all sides. The closer they fell, the more reality itself would twist. Seconds would feel like years compared to the world outside. In one direction, the universe would rush forward into a distant future, while in another, it would drag backward into the past. The spacecraft would be caught not only in space but in the trap of time. And then comes the tearing. Gravity does not pull evenly when one part of an object is closer to the trap than another. This difference is called tidal force, and in a cosmic trap, tidal forces become unbearable. The nose of the ship, being closer, feels a stronger pull than the tail. Slowly, then violently, the spacecraft begins to stretch, like dough being pulled apart. The crew feels the same effect. Feet tugged harder than heads, arms pulled wider than shoulders. The force increases until bones, muscles, and metal alike cannot withstand it. Scientists call this spaghettification, a name that may sound almost humorous, but hides one of the most horrifying fates possible. A human body, a spacecraft, a mountain, even a planet would be drawn into long, thin streams of matter, ripped down to the smallest particles before being swallowed entirely. The universe offers no mercy in these traps. No last-minute rescue, no clever maneuver, no secret exit. Once inside, all paths lead only inward, deeper into darkness. Even information itself cannot escape. This makes cosmic traps not only physical dangers, but also mysteries that hide their cause forever. What lies beyond the final veil of a black hole? Is there a center, a point where all matter collapses into something infinitely small? Or does the trap open into another space, another universe, a place forever cut off from ours? These questions make cosmic traps not only deadly, but also profoundly fascinating. They are the prisons of reality, but also its deepest secrets. Now imagine what such traps mean for the dream of exploration. Humanity hopes one day to travel across the galaxy, to send ships into regions no one has seen. But hidden among the stars are these invisible snares. They do not announce themselves with roaring fires or flashing lights. They simply wait. A starship could wander too close without knowing. A navigation error, a broken detector, or even a moment of overconfidence could send it drifting toward one of these silent killers. The nightmare is not only for the crew but also for those left behind. From Earth, mission control would watch the signals grow weaker, delayed, stretched, and then vanish. The ship would fade from reality, leaving behind only questions and silence. No wreckage, no return, no explanation, just absence. The human imagination has always filled the unknown with monsters, from sea serpents to dragons. But in space, the monsters are not creatures of flesh and blood. They are traps built from gravity and time. Their hunger is endless, not because they choose to feed, but because the laws of the cosmos make it so. For a crew facing one, the terror is not in fighting, but in realizing there is nothing to fight. The ship is caught in an embrace stronger than any weapon, held by forces that no strength can resist. It is a nightmare not of struggle, but of helplessness. These cosmic traps are not rare. Astronomers believe that our own galaxy, the Milky Way, may hold millions of black holes scattered like mines across its spiral arms. Some are the remains of massive stars that collapsed long ago. Others are giants lurking at the centers of clusters. At the very core of our galaxy lies a monster black hole with the mass of millions of suns. It sits there silently, bending the paths of nearby stars like toys on strings. A spacecraft crossing near the galactic center would have to navigate with extreme care, for the region is full of such traps, each capable of swallowing entire worlds. Even closer to Earth, smaller black holes may drift unseen, their presence betrayed only by the way they tug at nearby stars. To explore space fully, humanity must accept that these hidden snares are part of the landscape, as natural as mountains or oceans, but infinitely more deadly. The nightmare of these traps goes beyond destruction. They also challenge understanding. Every spacecraft that vanishes into one takes its knowledge with it. Instruments, data, recordings, none of it can be sent back once the boundary is crossed. To explore too close is not only to risk loss of life, but also loss of answers. The deepest secrets of gravity and the universe may lie inside, but no probe, no matter how clever, can bring them out. This makes the traps both barriers and invitations. They say, come closer, but not too close. Learn what you can from the edges, but never expect to see the heart. Yet, humanity has always been drawn to danger. Sailors once set out across seas where maps warned of monsters. Explorers crossed deserts and climbed mountains that had killed many before. In the same way, spacecraft will one day be sent near these cosmic traps, trying to skim the edges without falling in. Powerful detectors, careful planning and courage will all be needed, but always the nightmare will remain. The thought that one miscalculation, one slip, could send the ship spiraling past the point of no return. And when that happens, the universe itself becomes the executioner, pulling the explorers into a silence that no signal can pierce. The most chilling truth of all is that these traps are not rare exceptions, not flaws in the universe. They are part of its very structure. Gravity, the same gentle force that keeps our feet on the ground and holds planets in orbit, also builds these prisons when pushed to extremes. The same laws that let galaxies form also let them hide devourers at their cores. In a sense, cosmic traps are not accidents, but necessities, as natural as stars themselves. To explore the universe is therefore to accept that danger is woven into its fabric, and so the nightmare remains. Cosmic traps for spacecraft are the silent killers of the universe, waiting without malice, without intent, but with absolute certainty. To come too close is to vanish, body and machine, light and memory, swallowed by gravity's endless hunger. They remind us that space is not only a place of wonder and possibility, but also of danger beyond imagination. They are the dark truth behind the dream of exploration, that the universe, for all its beauty, has places where even the bravest ship must never tread. Could Gravastars power the universe is a question that drifts like a whisper across the minds of scientists who dare to step into the grey and shadowed regions between hard physics and imaginative speculation. Gravastars, those hypothetical siblings of black holes, are born from the same equations of general relativity that describe how matter bends space-time, but they take a very different turn. Instead of collapsing into a singularity that traps everything inside, a gravastar is thought to stop just short of that crushing end. At its heart, there may be a strange bubble of dark energy, an inner void that stretches space-time outward instead of drawing it in, wrapped in a shell of exotic matter that resists collapse. This makes gravastars one of the strangest and most mysterious ideas in astrophysics, objects that might hide unimaginable stores of energy waiting to be discovered. The question, then, is whether these hidden reservoirs could serve as engines capable of shaping the destiny of the universe itself. To grasp the possibility of gravastars powering the universe, one must first sit with the idea of how much energy might be contained inside such an object. When a massive star dies and collapses, gravity takes over, pulling everything inward. In the case of a black hole, this collapse continues until a singularity forms, a point where density is infinite and all our equations break down. For a gravastar, however, the collapse halts when the intense pressure and density of space-time itself triggers a phase change, much like water freezing into ice or boiling into steam, but on a cosmic scale. The matter of the star's core does not form a singularity but instead transforms into a vacuum-like energy field, often described as a bubble of dark energy. This inner region, sometimes thought of as pure vacuum energy, has properties that push outward instead of pulling inward. Surrounding it is a razor-thin shell of ultra-dense exotic matter that balances this outward push with an inward pull, holding the object together in a stable configuration. This balance between expansion and collapse suggests that gravastars may trap within themselves an ocean of vacuum energy, far greater than the energy stored in normal matter. Vacuum energy is not just emptiness. It is a restless sea of quantum fluctuations, a constant churning of energy at the smallest scales of reality. If gravastars are truly filled with such energy, then their interiors may contain more power than entire galaxies of stars combined. Here lies the temptation for cosmic speculation. Perhaps gravastars are not simply dead ends of stellar collapse, but hidden batteries of the universe, silent powerhouses whose reserves could, in theory, illuminate civilizations, drive cosmic processes, or even fuel the very expansion of the cosmos itself. One must reflect on the scale of energy hidden in vacuum energy to appreciate the enormity of this speculation. A single teaspoon of vacuum energy, if harnessed, could outshine the energy output of a planet's entire civilization for countless ages. If gravastars indeed harbour vacuum bubbles the size of collapsed stars, then we are speaking of an energy stockpile so vast that it stretches the imagination beyond ordinary limits. If there are millions or billions of gravastars scattered across galaxies, the total energy bound inside them may rival the energy of all luminous matter in existence. In such a picture, gravastars could be silent custodians of energy on a scale so massive that it overshadows the burning of stars, the collapse of supernovae, and even the rotation of galaxies. The idea that gravastars could power the universe naturally leads to comparisons with black holes. Black holes are often thought of as destructive, swallowing matter and light into a singularity from which no return is possible. Yet they too are paradoxically sources of energy, as seen in the form of Hawking radiation, accretion disks blazing with light, and powerful jets shooting across intergalactic distances. Gravastars, if real, may outmatch them in subtle ways. Instead of energy leaking from the edges like a candle burning down, gravastars could be self-contained furnaces of vacuum energy. The challenge is that their hidden energy is sealed behind layers of exotic matter, making them inaccessible unless some unimaginable process could tap into that store. Speculation invites one to imagine what might happen if such energy could indeed be tapped. Civilizations far older and wiser than our own might have learned how to extract the energy locked inside gravastars. To them, stars might seem like weak embers compared to the blazing potential of these dark, compact objects. They might build machines orbiting gravastars, harvesting power the way we gather sunlight from the sky. Whole galaxies might be engineered to revolve around these energy sources, their civilizations lit for eons by what to us seems like unreachable fuel. In this vision, gravastars become not just natural phenomena but pillars of cosmic engineering, secret engines turning the wheels of the universe's grand design. This speculation pushes deeper still when one considers the link between vacuum energy and dark energy, the mysterious force driving the accelerated expansion of the universe. Observations of distant supernovae, the cosmic microwave background, and the large-scale structure of galaxies reveal that the universe is not just expanding but accelerating in its expansion. The force behind this, called dark energy, makes up about 70% of the cosmos, yet it remains one of the greatest puzzles in science. Gravastars, filled with vacuum energy, might not be isolated curiosities but actual contributors to this cosmic acceleration. Each Gravastar could act like a tiny bubble of dark energy, and collectively, billions of them scattered across space might help drive the universe outward, fueling expansion on a grand scale. If this is true, then Gravastars are not just strange remnants of collapsed stars but participants in the largest scale drama of all, the shaping of cosmic destiny. They might form a hidden network of energy reservoirs that stitch the universe together, influencing its growth and its fate. Instead of being rare or marginal, Gravastars could be central players, their hidden interiors pulsing with the very energy that rules the evolution of space and time. The thought of this bends the mind, that the universe's future might be written in the interiors of objects we cannot even prove exist yet. One must also reflect on the possibility that Gravastars could represent not merely natural energy stores, but perhaps natural regulators of energy in the cosmos. The universe is a place of balances and cycles. Stars burn fuel, shine and die. Black holes swallow matter and energy. Galaxies spin in halos of dark matter, and expansion is driven by dark energy. Gravastars could fit into this pattern as regulators, preventing collapse into singularities while storing energy in vacuum form. They could act as cosmic safes, locking away vast sums of energy that might otherwise tear the fabric of space-time apart. Perhaps they are nature's way of balancing the books, storing what would otherwise be destructive force and turning it into silent, stable reservoirs that maintain cosmic order. The danger, of course, is that hidden energy is also a hidden potential catastrophe. If Gravastars are real, and if their interiors are filled with unimaginable energy, then what would happen if their balance were disturbed? If the thin shell of exotic matter were to rupture, the release of vacuum energy could trigger an explosion unlike anything seen in the universe. It would dwarf supernovae and gamma-ray bursts, releasing power capable of sterilizing galaxies. Such a thought is terrifying, for it would mean that Gravastars are not only possible power sources, but also cosmic bombs, ticking silently in the dark, awaiting only the wrong touch to unleash devastation. The universe, then, could be dotted with potential engines and potential doomsday devices, depending on how stable these strange structures truly are. The mystery deepens when one considers how Gravastars might be detected. Black holes can be inferred by the way they bend light, swallow stars, and produce X-ray emissions from matter falling into their gravity wells. Gravastars, on the other hand, would mimic many of these same effects. To an observer, they might appear identical to black holes, since their shells bend light in almost the same way. The only clues might lie in subtle differences, the absence of a true event horizon, unusual echoes in gravitational waves, or tiny shifts in how matter interacts near their surfaces. If future instruments, gravitational wave detectors more sensitive than those we have today, or telescopes capable of peering at cosmic edges with higher resolution, could pick out these differences, then perhaps we could confirm their existence. Only then could the speculation about their energy reservoirs move from wild imagination to scientific reality. Until that day, the question of whether Gravastars could power the universe remained suspended between dream and theory. Yet, one cannot help but linger on the images it creates. Whole civilizations gather power from Gravastars like bees around hives. The universe's expansion is pushed outward by countless bubbles of vacuum energy sealed inside them, cataclysms awaiting if one should rupture. And perhaps, most daring of all, the idea that the very engine of existence, the force that keeps galaxies racing apart, might not be some mysterious uniform field, but the collective breath of countless Gravastars whispering outward through space-time. To think of Gravastars in this way is to stand at the threshold of imagination and science. Gravastars are among the strangest ideas ever imagined in modern astrophysics. They were proposed as possible alternatives to black holes, those dark monsters of gravity that trap everything, even light itself. When black holes were first taken seriously as real objects in the universe, scientists quickly realized that they posed a deep puzzle. According to classical general relativity, a black hole once formed would remain forever, unless something collided with it or fed it more matter. But then the famous physicist Stephen Hawking showed in the 1970s that this picture was incomplete. By combining ideas from quantum theory with general relativity, Hawking discovered that black holes are not perfectly black. Instead, they emit tiny amounts of radiation, now called Hawking radiation. Over incredibly long spans of time, this radiation causes black holes to shrink, lose mass, and eventually evaporate completely. This discovery was shocking because it meant black holes are not eternal. They have a finite lifetime. The bigger the black hole, the longer it survives, but even the most massive ones will eventually disappear, though only after times far longer than the current age of the universe. This raised a haunting question. If black holes are not forever, then what about gravastars, these strange proposed cousins of black holes? Do they also leak away energy in the form of Hawking radiation, or do they evade this fate and endure forever in some stable form? To answer this, we must carefully look at what makes a gravastar different from a black hole. A black hole is defined by its event horizon, the ultimate boundary beyond which nothing can escape. It is this event horizon that is responsible for Hawking radiation, since the quantum fields in the universe behave strangely near it, creating particle-antiparticle pairs where one falls in and the other escapes as radiation. A gravastar, however, does not actually have an event horizon. Instead, it is theorized to have a very thin shell of exotic matter on its surface, and inside that shell is not a singularity or empty space, but rather a strange region dominated by vacuum energy, which behaves like a form of dark energy. The absence of a true horizon is critical. If there is no event horizon, then the standard mechanism of Hawking radiation may not apply at all. That would mean gravastars do not radiate away their mass in the same way black holes do. Instead of gradually evaporating, they might remain almost perfectly stable. If this is correct, gravastars could be effectively immortal, surviving indefinitely without fading away. But here we encounter a deep uncertainty. The theory of gravastars is not complete. It is a speculative model, one of many attempts to solve puzzles about the ultimate fate of collapsing stars. Whether gravastars radiate like black holes depends entirely on the exact quantum properties of their shell and interior, which no one fully understands yet. Some scientists suggest that gravastars might give off a faint glow of radiation, not because of an event horizon, but because of quantum effects in their exotic shell. Others think they might release occasional bursts of energy when matter falls onto them, mimicking some behaviors of black holes. Still, the central question remains: could a gravastar live forever? Imagine a massive star that collapses. Instead of becoming a black hole with an event horizon, it forms a gravastar. Its outer shell of exotic matter holds the star up against total collapse, while its inner vacuum energy keeps it inflated like a strange cosmic balloon. Time passes. The universe grows older, stars are born and die, galaxies collide, and black holes slowly radiate away through Hawking's process. But the gravastar sits there, unchanged, untouched by this slow bleeding of energy. Billions upon billions of years pass, and still it survives. If gravastars truly evade Hawking radiation, then in the unimaginably distant future, when black holes have evaporated and ordinary stars have long since burned out, gravastars might be among the last remaining structures in the universe. To appreciate the scale of this idea, consider that the evaporation time for a black hole as heavy as our Sun is around 10 to the power of 67 years, which is far, far beyond the current age of the universe, which is just under 14 billion years. For a supermassive black hole with a mass of millions or billions of suns, the evaporation time is even more staggering, up to 10 to the power of 100 years or more. If gravastars avoid this process, then their lifetimes are not just long, they are infinite compared to any black hole. They would represent eternal monuments in a universe where even the most massive black holes eventually vanish. But could it really be that simple? Some physicists argue that even without a horizon, gravastars might not be completely immune to quantum effects. Spacetime itself is a quantum field, and the exotic shell of a gravastar could in principle interact with those fields in subtle ways. This could create a tiny trickle of radiation, different from Hawking radiation, but still enough to slowly erode the gravastar over inconceivably long times. In this view, gravastars might not be eternal, but their lifespans could still dwarf those of black holes, making them last for unimaginable durations. Others suggest a different outcome. If gravastars truly contain a core of vacuum energy, then they may not be eternally stable at all. Vacuum energy itself might be unstable. capable of decaying into other forms of energy under the right conditions. If that decay happens, the Gravastar could suddenly release an enormous burst of energy, essentially exploding and disappearing in a dramatic flash. Instead of quietly evaporating like a black hole, a Gravastar might end in one colossal event. This leads us to an even more speculative thought. What if Gravastars, by avoiding Hawking radiation, actually hold on to their energy forever, until some quantum instability triggers them to collapse or explode? In that case, they might be cosmic time bombs lurking in the universe for billions of years before suddenly unleashing devastating outbursts. Some astronomers even wonder whether unexplained cosmic events, such as mysterious gamma-ray bursts, might in rare cases come from collapsing Gravastars rather than the usual explanations involving massive stars or neutron star mergers. When we compare Gravastars and black holes side by side, the contrast is fascinating. Black holes are defined, predictable in their long-term decay, and doomed to eventually vanish. Gravastars, if they exist, are undefined, mysterious, and possibly eternal. This makes them attractive theoretical objects, since they provide an alternative way for nature to avoid singularities and the paradoxes of information loss. Hawking's discovery of radiation created the so-called information paradox, where information about matter falling into a black hole seems to vanish forever. With Gravastars, that problem may not exist, since there is no true horizon to hide information behind. Matter falling onto a Gravastar might be preserved in some form in its shell or interior, never truly lost. If this is true, then Gravastars would not only evade Hawking radiation, but also solve one of the greatest paradoxes in physics. They would represent a kind of loophole in the laws of the universe, sidestepping both the destruction of information and the slow death through evaporation. Now imagine the far future once again. Picture a universe so old that black holes, those giants of gravity, have finally evaporated into nothing. The galaxies have spread apart into vast emptiness. Stars have all burned out, and only faint traces of radiation remain. In this silent darkness, Gravastars might still persist, unchanged since the day they formed. They would be ancient relics, older than the oldest black holes, lasting longer than any star, perhaps even outliving the very fabric of the universe itself. This possibility is both beautiful and unsettling. If Gravastars do not evaporate, then they represent a form of cosmic permanence, things that endure while everything else fades. They might become the last monuments in a dying universe, silent and dark, their exotic shells holding in their strange energy forever. If they can never release their energy, then they are like locked vaults, hoarding cosmic secrets eternally. But if they do one day collapse or explode, then they are ticking bombs, waiting for the right moment to unleash their hidden power. The truth is that we simply do not know. Gravastars are still a theoretical idea, not confirmed by observation. We cannot yet tell whether the strange radiation of quantum fields interacts with them the same way it does with black holes. We cannot measure their lifespans or watch them evolve over time. All we can do is imagine, calculate, and debate. But the question itself, do Gravastars evade Hawking radiation, is one of the most profound in modern astrophysics, because it touches on the nature of eternity, the fate of information, and the ultimate future of the cosmos. If they do evade it, then Gravastars might be immortal guardians of the universe, persisting through ages when all else is gone. If they do not, then they will eventually die, like black holes, but perhaps in stranger and more violent ways. In either case, they remind us that the universe still hides mysteries deeper than our current understanding, mysteries that stretch across time, span so vast that human imagination struggles to hold them. The vision of a cosmos where Gravastars endure while black holes vanish is a haunting one. It suggests a future where the most powerful and frightening objects we know, black holes, are only temporary, while their stranger cousins, the Gravastars, might be the true eternal rulers of the night. Whether they shine, collapse, or remain forever silent, Gravastars hold within them the possibility of immortality, a possibility that pushes us to rethink what it means for anything to live forever in a universe that itself may not. When we look at the universe through the rules of general relativity, black holes appear to be the ultimate prisons. They are regions of space where gravity is so strong that not even light can escape. Anything that falls inside is thought to be lost forever, hidden behind the event horizon, which is the invisible boundary that separates the inside of a black hole from the outside universe. But when we look at the same problem using quantum mechanics, which is the set of rules that governs the smallest parts of reality, a very different picture appears. Quantum physics tells us that information, in the form of the arrangement of particles and their states, should never be destroyed. This is not just a philosophical idea, it is a deep principle that lies at the heart of quantum theory. Yet black holes seem to destroy information, because once something falls inside, the outside world can never recover what went in. This conflict between relativity and quantum mechanics gave rise to the information paradox, and it has kept scientists puzzled for decades. The paradox became even stronger when Stephen Hawking, in the 1970s, showed that black holes are not completely black. According to Hawking's calculations, black holes emit radiation due to quantum effects near the event horizon. This radiation, now called Hawking radiation, slowly drains energy from the black hole, causing it to shrink over unimaginably long periods of time. Eventually, the black hole could evaporate completely. But here lies the problem. If the black hole disappears, then all the information about the things that fell into it is gone too, erased from the universe. That would break the fundamental laws of quantum mechanics, which say that information is never truly lost. It is like writing a book, throwing it into a fire, and watching the book burn. The paper is gone, the ink is gone, but if you are careful enough, you can still, in principle, reconstruct what was written from the smoke, the ash, and the heat. In quantum mechanics, the universe keeps the records no matter how scrambled they become. But if a black hole vanishes without leaving behind a trace of the information it swallowed, it is as though the universe has torn out pages of its own history. That is why the paradox is so disturbing. Now comes the idea of gravastars. Gravastars, or gravitational vacuum stars, are a bold alternative to black holes. They were proposed as a way to avoid the information paradox and to show that perhaps the universe has a trick up its sleeve. A gravastar looks very much like a black hole from the outside. It is extremely compact, incredibly heavy, and surrounded by gravity so strong that anything coming too close would find it impossible to escape. But unlike black holes, gravastars do not have a singularity at the center or an event horizon. Instead, they are thought to have a very thin shell made of exotic matter, surrounding a core filled with something even stranger, a bubble of dark energy or vacuum energy. In this picture, the collapsing star never truly forms a black hole. Instead, the collapse stops just before an event horizon can form, and the shell of exotic matter stabilizes the structure. The result is an object that fools the outside observer into thinking it is a black hole, but at its heart it is something entirely different. If gravastars exist, they could provide an elegant way out of the information paradox. Since gravastars have no true event horizon, information that falls toward them is not lost forever. The shell of exotic matter and the vacuum core could interact with infalling matter in ways that allow the information to be stored, scrambled, or even radiated back out over time. The object may still appear black from far away, but in principle, the information is not destroyed. It could remain encoded in the complex structure of the gravastar, or it might eventually leak out in some subtle form. This means that gravastars would obey the rules of quantum mechanics while also respecting the predictions of relativity. They would solve the paradox by showing that what we thought were black holes might instead be these mysterious hollow stars. To appreciate how radical this idea is, one must remember the long struggle between quantum mechanics and relativity. Albert Einstein's general relativity describes the universe on large scales, the movement of planets, the bending of light by gravity, and the dynamics of galaxies. Quantum mechanics describes the small scales, the behavior of atoms, particles, and fields. Both theories work spectacularly well in their own domains, yet when we try to put them together in extreme places like black holes, contradictions arise. The information paradox is one of those contradictions, and for decades physicists have wondered whether the solution lies in changing relativity, changing quantum mechanics, or inventing something entirely new. Gravastars offer a middle path. They keep relativity intact by explaining why ultra-compact objects look like black holes, but they also keep quantum mechanics intact by avoiding information loss. Imagine a spaceship approaching what appears to be a black hole. To distant observers, the spaceship seems to slow down and freeze at the edge of the event horizon, never quite falling inside. From the perspective of the crew, however, they cross the horizon and plunge inward. If the object is truly a black hole, the crew and their ship are lost to the outside universe. But if it is a gravastar, things might be very different. There is no true horizon, just a strange shell of exotic matter. As the ship comes close, it would interact with this shell, perhaps being shredded or transformed, but the information about its structure would not vanish into a singularity. Instead, it would be imprinted on the shell or absorbed into the vacuum bubble. The details are deeply theoretical and far beyond current experiments, but the key point is that nothing is lost forever. The universe keeps the record, even if it is hidden in a strange and alien form. The Gravastar model has other advantages too. Black holes suffer from the problem of singularities. At the very center of a black hole, relativity predicts that density and curvature become infinite, meaning that the equations break down and stop making sense. Many physicists believe that true infinities do not exist in nature. They are a sign that our theory is incomplete. By removing the singularity, gravastars give us a more consistent picture. Instead of infinite density, the center is filled with vacuum energy, which is strange but not mathematically impossible. This makes gravastars not just a potential solution to the information paradox, but also a possible answer to the problem of singularities. Of course, the big question is whether gravastars really exist in the universe, or whether they are just a clever mathematical trick. To answer that, scientists are searching for signs that could distinguish gravastars from black holes. The differences might be very subtle. For instance, the way gravitational waves echo after two of these objects collide might reveal whether they have horizons or shells. Black holes would give off a clean signal as they merge and then fade away, while gravastars might produce faint echoes caused by waves bouncing off their shell. Similarly, the way light bends around them, or the way matter swirls in the disk of gas surrounding them, might carry hidden clues. These are not easy measurements to make, but new observatories, such as gravitational wave detectors and advanced telescopes, are beginning to test these ideas. The information paradox has driven physicists to wild proposals. Some argue that information escapes from black holes in a subtle way through Hawking radiation, which somehow encodes the history of what fell inside. Others argue for new structures like firewalls, blazing barriers of energy that sit just outside the horizon and destroy anything that falls in, though this idea creates new contradictions of its own. Some physicists suggest that the entire concept of space-time may need to be rethought at a fundamental level. Gravastars, in this landscape of bold speculation, stand out because they are relatively conservative. They do not demand that we throw away relativity or quantum mechanics. Instead, they say that perhaps we misinterpreted what happens when stars collapse, and the universe gives us gravastars instead of true black holes. The beauty of this proposal is that it gives us hope that information is never truly lost. For centuries, humans have sought to understand whether the universe is lawful, whether it plays fair, or whether it allows things to simply disappear without explanation. The information paradox threatened that faith by suggesting that black holes could act like cosmic shredders of history. Gravastars reassure us that even the darkest corners of the cosmos may still respect the deep rules of physics. The price is that we must accept objects stranger than anything we have ever seen, with shells of exotic matter and hollow hearts filled with vacuum energy. But then again, the universe has never been shy about surprising us. To put the timescales into perspective, consider how long it would take for a black hole to evaporate through Hawking radiation. A black hole the mass of our Sun would take about 10 to the power of 67 years to vanish. That is a 1 followed by 67 zeros, a timescale so vast that it dwarfs the current age of the universe, which is about 1.4 times 10 to the power of 10 years. Larger black holes would take even longer, up to unimaginable stretches of time. If information really does vanish with the black hole, then the universe would be breaking its own laws for all those countless years. Gravastars, by avoiding evaporation in the first place, would avoid the problem entirely. They could persist indefinitely, storing information for eternity. One can also think of gravastars as cosmic vaults. When matter falls into them, it is not destroyed but locked away in the strange physics of the shell and vacuum interior. Perhaps one day, if our understanding deepens, we might even imagine ways of retrieving or decoding that information. Of course, that is pure speculation today, but it shows the kind of possibilities that emerge when we try to solve the paradox. Gravastars turn a hopeless problem into an open door for new ideas. There is also a poetic side to this idea. The universe is often described as a grand book written in the language of physics. Every particle, every atom, every star is a letter in that book, and the laws of quantum mechanics ensure that no letter is ever truly erased. The information paradox threatened to tear pages out of the book, leaving gaps in the story. Gravastars restore those pages, telling us that the universe's story remains whole, even if the writing is hidden behind dark and mysterious covers. They transform black holes from destroyers of history into keepers of secrets. In the end, the information paradox problem is not just a technical debate among physicists. It strikes at the heart of what it means to understand the universe. If information can vanish without a trace, then science itself faces a limit, because we could never be certain that the universe's rules are consistent. But if Gravastars or some other solution preserves information, then the universe remains lawful and knowable, no matter how strange it appears. Gravastars may or may not turn out to be real, but by exploring them, we're forced to ask the deepest questions about the nature of space, time, and reality itself. The search for answers continues. Perhaps one day, gravitational wave observatories will detect echoes that reveal the presence of Gravastar shells. Perhaps future telescopes will catch subtle patterns of light that betray their hollow nature. Or perhaps black holes will triumph after all, and we will find that information does escape them in some mysterious way. Whatever the outcome, the struggle with the information paradox has already reshaped our thinking. It has led us to consider that the universe might be stranger and more subtle than anyone dared to imagine. And so Gravastars, these ghostly alternatives to black holes, stand as one of the most daring ideas in modern science. They promise to solve one of physics' greatest puzzles by showing that the universe does not erase its own history. They remind us that even in the darkest depths of space, the laws of physics still whisper their secrets, waiting for us to listen closely enough to hear them. At the heart of nearly every galaxy, including our own Milky Way, there lies a powerful and invisible object that shapes the stars, gas, and dust swirling around it. For a long time, scientists have believed that these central objects are supermassive black holes, colossal monsters with masses millions or even billions of times greater than our Sun. These black holes are thought to act as engines that drive the motion of stars in their galaxies, and sometimes produce dazzling jets of energy that can outshine everything else in their cosmic neighborhood. But in recent years, a bold new idea has surfaced, one that challenges this long-standing belief. What if, instead of black holes, the true rulers of galactic cores are gravastars? A gravastar, short for gravitational vacuum star, is a strange and exotic object predicted by certain theoretical models. Unlike a black hole, which is said to trap everything, including light behind its event horizon, a gravastar does not collapse into a singularity. Instead, it is believed to have a shell of exotic matter that holds back its collapse, enclosing a core filled with a special kind of vacuum energy. This makes it hollow at the center, unlike the crushing singularity of a black hole. Gravastars have been proposed as a possible alternative to black holes, solving some of the paradoxes that black holes create in physics. The big question is whether these hypothetical objects could actually exist at the centers of galaxies, taking the place of black holes, and if so, what kind of universe would we be living in? To understand this, it helps to look at how galaxies behave. Astronomers have found that stars near the center of galaxies orbit at incredible speeds. In the Milky Way, for example, stars close to the core are moving so fast that only an object millions of times the mass of the Sun could possibly hold them in place with gravity. The central object has been named Sagittarius A, and it has been considered a supermassive black hole for decades. But when scientists study the behavior of Sagittarius A in detail, certain mysteries appear. For example, the energy bursts it sometimes produces are difficult to fully explain. Some researchers have wondered if what we are actually seeing is not a black hole, but something more subtle and exotic. A gravastar might be able to mimic a black hole so closely that even powerful telescopes would struggle to tell the difference. The first big difference between a black hole and a gravastar lies in the event horizon. A black hole has an event horizon, a point beyond which nothing can escape. Once matter or light crosses that invisible boundary, it is lost forever, pulled into the singularity at the center. But a gravastar does not have such an event horizon. Instead, It has a thin outer shell of exotic matter that resists collapse. If matter falls toward a gravastar, it might crash against this shell rather than disappearing into a singularity. From the outside, however, this difference would be very hard to detect, because the shell would still trap most of the light and radiation, making it look nearly as dark as a black hole. This means that when astronomers point their instruments at galactic cores, they could be staring not at black holes but at gravastars, and they might never know unless they find a subtle clue that distinguishes one from the other. One of the strongest arguments in favour of gravastars is that they avoid the so-called information paradox. In black hole theory, when matter falls past the event horizon, all information about that matter is lost, at least from the point of view of the outside universe. This creates a clash with the laws of quantum mechanics, which say that information cannot be destroyed. For decades, physicists have wrestled with this paradox, searching for ways to reconcile black hole behaviour with quantum theory. Gravastars sidestep the problem by never allowing matter to truly vanish into a singularity. Instead, the exotic shell and vacuum energy inside the gravastar might store or recycle the information, keeping the laws of physics intact. If galactic cores were gravastars, then the universe might be more consistent with quantum rules than if they were true black holes. Of course, if gravastars sit at the hearts of galaxies, their influence would not stop at the philosophical level of paradoxes. They would also change the way galaxies grow and evolve. Supermassive black holes are often thought to play a crucial role in shaping galaxies, controlling star formation by spewing out enormous jets of radiation and streams of particles. These outflows can heat up surrounding gas, preventing it from collapsing into new stars, or sometimes trigger star formation in certain regions. If gravastars replace black holes in this role, then the mechanics of how these outflows are generated could be very different. Perhaps the exotic shells of gravastars reflect and focus in falling energy in unusual ways, creating bursts that appear similar to black hole jets, but actually come from very different processes. This means that when astronomers look at distant galaxies with blazing cores, they might be witnessing the work of gravastars rather than black holes. To test this idea, scientists have tried to imagine what kinds of signatures gravastars might leave behind. One possibility is in gravitational waves, the ripples in space-time first predicted by Albert Einstein and finally detected in the year 2015. When two black holes collide, they send out gravitational waves that can be detected by instruments like LIGO and Virgo. If two gravastars collided instead, the signal might be slightly different. For instance, instead of a clean merger into a larger black hole, the collision of two gravastars might produce echoes in the gravitational wave pattern caused by the exotic shells bouncing energy back and forth. Detecting such echoes could reveal the true nature of these cosmic objects. If galactic cores are gravastars, then one day we might capture the smoking gun evidence in the form of these unusual gravitational wave signals. Another possible signature comes from the Event Horizon Telescope, the worldwide network of radio telescopes that produced the famous first image of a black hole in the year 2019. That blurry orange ring, showing the shadow of the black hole in the galaxy Messier 87, was hailed as proof of black holes' existence. But some researchers argue that a gravastar could produce almost the same image. The key difference might lie in the details of the brightness of the ring, or the way light bends around the object. Future, sharper images might be able to tell the difference. If one day we look at Sagittarius SC or Messier 87 again with even clearer vision, and find that the image does not quite match black hole predictions, it could point toward gravastars as the real explanation. The concept of gravastars also sparks fascinating speculation about the deepest workings of the universe. If the centers of galaxies are gravastars, then the vacuum energy inside them might connect to the same mysterious energy that drives the expansion of the universe, known as dark energy. In this sense, galactic cores might not just be gravitational anchors holding galaxies together, but also reservoirs of the very force that shapes the cosmos on the larger scales. Perhaps every gravastar is like a pocket of dark energy, and together they form a hidden network influencing the fate of the universe. This would make gravastars not only black hole mimics, but also keys to solving the riddle of why the universe is expanding faster and faster. Skeptics, of course, point out that black holes already explain much of what we see without needing to invent new exotic objects. The behavior of stars orbiting galactic centers, the radiation from accretion disks, and the outflows of energy all fit well with black hole models. To replace black holes with gravastars, scientists would need very strong evidence, something that cannot be explained by black holes alone. Right now, such evidence is lacking, and gravastars remain speculative. Still, science has always advanced by questioning old assumptions and considering radical alternatives. The very idea of black holes was once dismissed as too strange to be real, and yet today they are widely accepted. Gravastars may follow a similar path, moving from speculation to serious consideration as new observations come in. If galactic cores are gravastars, then the story of cosmic history might need to be rewritten. Galaxies formed in the early universe when clouds of gas collapsed under gravity, and supermassive objects grew rapidly at their centers. If those objects were gravastars instead of black holes, then the early universe may have been filled with shells of exotic matter and bubbles of vacuum energy rather than singularities. This would mean that the universe's first great engines of growth were not as destructive as once thought, but instead strange structures that recycled matter and energy in unusual ways. The galaxies we see today, from spirals like the Milky Way to giant ellipticals, may carry the fingerprints of gravastars hidden in their cores. Even the question of life in the universe could be touched by this possibility. Black holes are often seen as ultimate dead ends, swallowing everything without a trace. But gravastars, by preserving information and perhaps interacting differently with matter and energy, might allow for a more balanced cosmic ecosystem. The jets and radiation from galactic cores could still be dangerous, but they might also be more controlled or varied if gravastars are behind them. Civilizations looking at the stars might one day realize that the very structures they thought were monstrous devourers are instead complex engines of balance, sustaining the cosmic order in ways we never imagined. The debate between black holes and gravastars at galactic cores is not just about astronomy. It is also about our imagination and willingness to question what we think we know. Black holes have become a symbol of the universe's mystery, an ultimate boundary where known laws break down. Gravastars offer a different vision, one in which those boundaries are illusions, hiding deeper truths that are stranger but also more consistent with the rules of physics. Perhaps in the coming decades, with better telescopes, sharper gravitational wave detectors, and deeper theoretical insights, we will finally know whether the hearts of galaxies are true black holes or the hollow shells of gravastars. Until then, every observation we make keeps this cosmic mystery alive, reminding us that the universe is always more surprising than we expect. The idea that gravastars could somehow be linked to the expansion of the universe through dark energy is both mysterious and exciting. Gravastars, or gravitational vacuum stars as they are fully called, are theoretical cosmic objects that some scientists have suggested as possible alternatives to black holes. Unlike black holes, which trap everything that falls beyond their event horizons, gravastars are imagined as strange hollow spheres where an outer shell of exotic matter keeps a vacuum-like interior from collapsing. Inside that vacuum-like space, it is believed that a special form of energy, something very similar to what we call dark energy, might be at work. If this is true, then gravastars may not only challenge the long-standing belief that black holes dominate the centers of galaxies, but they could also connect directly to the greatest mystery in modern cosmology: the fact that the universe is not just expanding, but expanding faster and faster as time goes on. Dark energy itself is a term we use to describe whatever it is that is making the universe's expansion accelerate. For many decades, scientists thought that after the Big Bang, the expansion of the universe would slowly decelerate because gravity should be pulling everything back together. But in the late years of the 20th century, astronomers using distant exploding stars known as supernovae discovered that the opposite is happening. Instead of slowing down, the galaxies are rushing away from one another at an increasing rate. The unknown cause of this acceleration was named dark energy. It is called dark, not because it is literally black or shadowy, but because it is invisible, mysterious, and unlike any ordinary form of energy we know. Today, scientists estimate that nearly 70% of the entire energy content of the universe is made up of dark energy, while matter, both normal and dark matter, makes up the remaining 30%. This means that the vast majority of the cosmos is dominated by something we cannot see or directly detect, and yet it shapes the fate of the universe itself. Now, the intriguing possibility arises when we compare the properties of gravastars with what we know about dark energy. The inside of a Gravastar is thought to be filled with what physicists call a false vacuum, or de Sitter vacuum, a state of space that resists collapse with a kind of repulsive pressure. This repulsive pressure is mathematically very similar to the way cosmologists describe dark energy on the scale of the universe. In other words, what prevents the Gravastar from collapsing into a singularity is the same type of force that pushes galaxies away from one another. If Gravastars really exist, then each one could be like a small laboratory of dark energy locked inside a cosmic shell. Instead of black holes swallowing matter and leading to a point of infinite density, Gravastars would be cosmic objects whose very existence relies on dark energy's ability to counteract gravity. This raises breathtaking questions. Could the countless black hole candidates we have identified in galaxies actually be Gravastars hiding in plain sight? If so, then the universe could contain trillions upon trillions of small pockets of dark energy-like interiors, scattered across space wherever massive stars collapsed. If every Gravastar contains a region of repulsive vacuum energy inside it, then their combined effect might contribute to, or even explain why the universe as a whole is accelerating. Rather than dark energy being some mysterious fluid spread evenly everywhere, perhaps it is partly contained and stored within these strange cosmic shells. One can imagine the history of the universe under this possibility. In the first billions of years after the Big Bang, stars formed, burned their fuel, and many of the most massive ones collapsed at the end of their lives. Traditionally, we say they formed black holes, but if instead, at least some of them formed Gravastars, then each one would have created a new bubble of repulsive vacuum energy sealed inside a crust of exotic matter. With every passing epoch, more Gravastars would form as more stars died, and this would mean that the universe would gain more and more bubbles of vacuum energy. The total effect would be an increasing outward push on the fabric of space itself, reinforcing the cosmic acceleration. This would tie the birth and death of stars directly to the destiny of the universe as a whole, a link that makes the story of cosmic evolution even more interconnected. Another interesting aspect is that Gravastars may avoid the information paradox that troubles black holes. Black holes, according to the traditional picture, trap information forever behind their event horizons, which conflicts with quantum theory that says information cannot be destroyed. Gravastars, with their dark energy-like interiors, may not have such horizons. Instead, the exotic matter shell and repulsive vacuum prevent full collapse. If this is the case, then the connection to dark energy is not just about cosmic acceleration, but also about the consistency of physics itself. Perhaps the laws of nature prefer Gravastars because they avoid contradictions, and in doing so, they reveal why the universe is dominated by this mysterious repulsive energy. The mathematics behind this idea also has elegance. When cosmologists describe dark energy, they often use what is called the cosmological constant, a term Albert Einstein originally introduced into his equations of general relativity. This constant represents a uniform energy density filling all of space. Inside a Gravastar, the vacuum interior behaves exactly like a miniature cosmological constant. It creates negative pressure that pushes outward, keeping the shell from collapsing. The fact that the same mathematical concept works on both the small scale of a Gravastar and the large scale of the cosmos suggests a deep unity. It is almost as though the universe is built on repeating patterns, where the same type of energy governs both the structure of individual objects and the evolution of the cosmos itself. Skeptics may argue that even if Gravastars exist, their combined influence would be tiny compared to the vast amount of dark energy needed to explain cosmic acceleration. After all, the universe is unimaginably large, and most of it is empty space not filled with Gravastars. But this may not be a decisive objection. If the interiors of Gravastars are truly regions of dark energy like vacuum, then their contributions could interact with the larger cosmic background. In fact, the creation of Gravastars could act as seeds, enhancing the presence of dark energy across the cosmos. In such a picture, the universe does not have dark energy as a separate, independent field, but as something naturally produced whenever matter collapses under its own gravity, but refuses to form a singularity. The death of stars would literally be feeding the expansion of the universe. Another way to think about this is to imagine the universe as a giant tapestry of space and time. Normally we imagine gravity as creating dents or curves in this tapestry, pulling matter together. But dark energy is like a stretching force that pulls the threads apart. Now imagine that scattered across this tapestry are gravastars, each one like a bead of tension that keeps pushing outward from within. They do not collapse, and instead their insides keep the surrounding fabric stretched. Over time, as more gravastars appear, the whole tapestry experiences more stretching. This mental picture captures how local processes like star collapse could add up to global effects like cosmic acceleration. The connection between gravastars and dark energy also opens fascinating questions about the fate of the universe. If the acceleration continues forever, galaxies will drift farther and farther apart, and eventually, billions of years from now, even the closest galaxies will vanish beyond our horizon. Stars will die, and the universe will become a dark and cold place. But if gravastars keep forming, then the dark energy-like interiors will multiply. Could this mean that the universe will accelerate even faster than we predict today? Could the presence of gravastars change the ultimate outcome, leading perhaps to a scenario known as the Big Rip, where space itself is torn apart? Or could they balance the acceleration in some subtle way, preventing such a catastrophe? The truth is, we do not know, but the possibilities highlight how linking these strange objects to dark energy makes the cosmic story far richer and more dramatic. There are also observational challenges. So far, astronomers cannot easily tell the difference between black holes and gravastars. Both would appear as invisible regions surrounded by glowing disks of hot matter, and both would produce powerful jets and radiation. However, the internal structures are very different. If we can one day detect tiny differences in how gravitational waves behave when two of these objects collide, or if we can see unusual patterns in the shadows of supposed black holes, then we might be able to confirm the existence of gravastars. If that happens, and if their interiors really are regions of dark energy like vacuum, then we would have a direct experimental link between astrophysics and cosmology. The mystery of dark energy would no longer be just a property of empty space, but a tangible feature of actual objects scattered across the cosmos. Even at a philosophical level, the connection is thought-provoking. Dark energy, in many ways, represents the unknown frontier of physics. It challenges our understanding of reality itself because it acts like a property of space rather than of particles or fields in the usual sense. Gravastars, on the other hand, challenge our understanding of collapse, death, and rebirth of stars. To think that these two mysteries may not be separate but two sides of the same coin is almost poetic. It suggests that nature does not waste its tricks. The same repulsive force that saves stars from becoming singularities may also drive the universe to grow without end. This idea also reshapes our view of cosmic balance. In ordinary thinking, gravity pulls things together, while dark energy pushes them apart. These are opposite and competing influences. But in gravastars, the two are not simply opposed. They cooperate. Gravity tries to crush the star, but instead of winning completely, it gives rise to a new state of matter and vacuum that resist collapse. Out of destruction comes stability, and that stability itself is powered by the same type of energy that rules the cosmos. It is as though every gravastar is a miniature version of the cosmic struggle between attraction and repulsion, a reminder that the forces shaping the universe are also at play inside individual stars. When we look at the universe in this light, even familiar astronomical events take on new meaning. The collapse of a star is no longer just the end of its life, it is the beginning of a new cosmic laboratory, a place where the mysteries of dark energy are encoded and preserved. Every gravastar could be thought of as a monument to the hidden connection between death and creation, between the local and the universal. It makes us see the night sky differently, as not just filled with stars and galaxies, but perhaps filled with countless hidden chambers of dark energy, quietly contributing to the expansion of all that exists. The connection also challenges us to rethink the role of humans in the cosmos. We are creatures who evolved on a small planet orbiting a medium-sized star, yet we're daring to imagine links between the collapse of giant stars and the acceleration of the entire universe. This is a bold act of imagination, but it is also a testament to the human spirit of inquiry. Gravastars and dark energy may seem like abstract concepts far beyond our everyday experience, yet they may hold the key to the ultimate fate of everything. By studying them, we are in a sense trying to read the universe's diary, to glimpse the hidden logic that governs its story from beginning to end. To grasp how vast this idea is, consider numbers. The universe is about 13.5 billion years old, and galaxies contain billions of stars. If even a small fraction of those stars ended their lives as gravastars, then we are already talking about trillions of these objects scattered throughout space. Each one would be a sealed chamber of dark energy, contributing its repulsive influence. Imagine a cosmic ocean dotted with countless floating lanterns, each one glowing not with light, but with invisible pressure. Together, they would shape the currents of the whole ocean, guiding the flow of cosmic expansion. This is the scale on which the Gravastar dark energy connection operates. Of course, many mysteries remain. We do not yet know if exotic matter, required to stabilize gravastars, really exists. We do not yet know if the false vacuum inside a gravastar truly mirrors the properties of dark energy on the larger scales, and we do not yet know whether gravastars are abundant or rare. But the beauty of science lies in asking these questions and following where the evidence leads. If the universe has given us this hidden connection, then it's up to us to uncover it, piece by piece, observation by observation, idea by idea. A gravastar is a hypothetical object that is suggested as an alternative to black holes, while a wormhole is a tunnel-like structure that might connect two distant regions of space, or even two separate universes. Both of them belong to the world of theoretical physics, a world where imagination and mathematics meet, where the laws of space and time are stretched into shapes that go far beyond ordinary experience. When people speculate about their possible role in exotic space travel, they are really imagining ways in which the deepest mysteries of the universe could one day be harnessed to allow journeys that today seem impossible. To think about this is to stand at the edge of human knowledge and peer into possibilities that might reshape the future of exploration forever. A gravastar, short for gravitational vacuum star, is an idea that tries to solve the puzzles that come with black holes. Black holes are regions where gravity has become so strong that nothing, not even light, can escape. Yet black holes create serious problems for physics, such as the information paradox, the singularity at their center, and the way they distort space-time in seemingly infinite ways. Some scientists have wondered if nature avoids these problems by never truly making a black hole, but instead creating a gravastar. In this picture, when a massive star collapses, instead of squeezing into a singularity, it creates a shell of extremely exotic matter around a hollow core filled with what resembles dark energy or a vacuum-like state. From the outside, a gravastar would look almost identical to a black hole, but deep inside it would be very different. This is not just a small change. It could mean that instead of swallowing information forever, a gravastar could preserve it, and instead of being a cosmic dead end, it could be a strange container of energy and structure. Now, if gravastars exist, they might play a role in more than just astrophysics. They could serve as anchors or even as engines for exotic space travel. Why? Because the very materials and energies they are made of could hold the keys to manipulating space-time itself. Exotic matter, which is required to stabilize wormholes and make faster-than-light travel possible, is also the kind of substance thought to hold up the shell of a gravastar. This connection between gravastars and wormholes is not just a coincidence. It suggests that these two exotic ideas might actually be two sides of the same coin. Where one appears, the other might not be far behind. If the universe does allow gravastars, it might also allow wormholes, and together they could form a natural toolkit for bending the geometry of reality. A wormhole is often imagined as a tunnel through space-time. It was first described in the early 20th century by Albert Einstein and Nathan Rosen, which is why it is sometimes called an Einstein-Rosen bridge. Imagine folding a sheet of paper so that two far-apart points touch, and then poking a hole through the fold to connect them. That is how a wormhole is often explained, though in reality the mathematics is much more complicated. If wormholes exist, they could allow instant travel between points separated by vast distances. A journey to a star tens of light years away could become as short as stepping through a door. But wormholes are unstable. They collapse almost instantly unless held open by negative energy or exotic matter. This is where gravastars might come in. If the shell of a gravastar truly is made of exotic matter, it could, at least in theory, provide the stabilizing ingredient needed to keep a wormhole open long enough for passage. Speculating about using gravastars and wormholes for space travel means imagining technologies that can manipulate them. For example, if a civilization were able to harness a gravastar, it might be able to peel away or use part of its exotic shell to feed and stabilize a wormhole, Or, perhaps even more astonishing, gravastars themselves might naturally act as gateways to wormholes. Some theorists suggest that what looks like a gravastar from the outside could actually be a wormhole throat in disguise. Instead of being a hollow star-like body, it could be the mouth of a tunnel leading elsewhere in the universe. If this is the case, then the universe could be scattered with hidden doors, waiting for someone advanced enough to open them. Now, picture what this means for space travel. Our current rockets are painfully slow. Even travelling to the nearest star system, Alpha Centauri, would take tens of thousands of years with conventional technology. But if wormholes stabilised by gravastar-like structures exist, then it might be possible to leap across the galaxy in seconds. Imagine a spacecraft approaching what appears to be a black hole, but instead of being destroyed, it enters into a carefully stabilised gravastar wormhole system and emerges light years away. Entire civilizations could spread across the stars, not in millennia, but in mere moments. This would change not only how we travel, but how we think about distance and time itself. There are, of course, enormous challenges. For one, we do not yet know if gravastars exist at all. They are still only theoretical, proposed as an alternative to black holes. Detecting them would be difficult because they mimic black holes so closely. Observing a gravastar wormhole connection would be even harder. Then there is the matter of energy. The exotic matter required to keep a wormhole open is not something we can create in large amounts. Even tiny amounts of negative energy are incredibly difficult to produce in laboratories. To stabilize a wormhole large enough for a spacecraft, the energy requirements might be beyond anything we can currently imagine. Yet history has shown that what seems impossible in one century can become practical in another. The idea of heavier-than-air machines flying across oceans once seemed absurd, and yet airplanes now circle the globe every day. Another possibility is that gravastars and wormholes are not built by us, but are natural features of the universe. If so, then advanced space travel might mean learning to locate and navigate them, rather than trying to build them from scratch. The galaxy could contain hidden networks of natural wormholes, stabilized by gravastars or exotic matter fields, waiting like ancient highways. Civilizations far older than ours might already know how to use them. Perhaps this is one reason why the cosmos appears so quiet. If other beings are travelling through hidden wormhole corridors, they might not leave many traces in normal space. The silence of the stars could be hiding a bustling network of travel routes beyond our current perception. The speculative link between gravastars and wormholes also raises deeper questions about the structure of the universe. For instance, if wormholes can connect not only 2 points in space, but also 2 points in time, then gravastars could be gateways not just to distant stars, but to the past or the future. Exotic space travel could then also become exotic time travel. The implications of this are staggering. Civilizations might step through a gravastar-stabilized wormhole and emerge in an entirely different era. They could witness the birth of galaxies or travel to the heat death of the universe. This adds another layer of wonder, but also danger, since tampering with time raises paradoxes that physics does not yet know how to resolve. If gravastars truly exist as alternatives to black holes, then their interiors might hold the secret to wormhole creation. The vacuum-like energy at their cores could be similar to the kind of energy that drives cosmic expansion, the same mysterious dark energy that makes up most of the universe. If so, then tapping into this energy might allow us to shape space-time itself. In that sense, gravastars might not just be gateways to wormholes, they might be cosmic laboratories, where the very tools of faster-than-light travel are stored, waiting for a mind clever enough to unlock them. There is also a poetic quality to this speculation. For thousands of years, humans have looked up at the stars and wondered how to reach them. Our myths told of gods and heroes crossing the heavens with ease. Wormholes and gravastars are the scientific versions of those ancient dreams, giving a possible physical mechanism for travelling across the cosmos as swiftly as stepping through a doorway. They embody the same longing but translated into the language of physics and mathematics. Yet speculation must also be balanced with humility. Gravastars may turn out not to exist. Wormholes may remain forever unstable. The universe may deny us the shortcuts we dream of, leaving us with the slow crawl of rockets and generations-long journeys. But even if this is the case, the act of imagining gravastars and wormholes as tools for space travel pushes human thought forward. It challenges us to think bigger, to consider possibilities beyond our current reach, and to keep striving toward new horizons. Sometimes the path to discovery begins with daring to imagine what seems impossible. Still, there are hints in the mathematics that keep the speculation alive. Solutions to Einstein's equations of general relativity do allow wormhole-like structures. Quantum field theory does suggest the existence of negative energy, at least in principle. Exotic matter is strange, but not forbidden. Gravastars offer an elegant way to avoid the singularities that trouble black hole physics. None of these ideas have been ruled out, and so long as they remain possible, the door is open for speculation. If the laws of physics truly allow gravastars and wormholes, then space travel might one day be transformed into something far beyond rockets and fuel. Imagine again a spacecraft drifting toward what seems like a black hole. Its crew braces for destruction, but instead of being crushed, the craft slips through a shimmering shell of exotic matter. Inside, there is no singularity, no crushing end, but a corridor of warped space. Lights flicker as space-time itself bends around them. Moments later, the ship emerges, not destroyed, but orbiting a star on the far side of the galaxy. What today seems like science fiction could one day become science fact if gravastars and wormholes truly can be used for travel. That vision, however distant, is why scientists and dreamers alike continue to speculate.